Hello there, and welcome to our quiet journey through some of NASA's most puzzling discoveries. Tonight, we're going to start with something that arrived unannounced and changed the way we think about what moves between the stars. I'm talking about visitors from beyond our solar system, not the science fiction kind, but real objects that have traveled for millions of years across the darkness of space before finally, by chance, passing close enough for us to notice them. Before we begin, I'd love to know where you're listening from right now and what time it is where you are. It's interesting, isn't it? We're about to talk about objects that have been wandering the galaxy longer than complex life has existed on Earth, and yet here we are, sharing this moment together from wherever you happen to be. If this kind of gentle exploration interests you, I'd be grateful if you considered subscribing. It helps this quiet signal reach other curious minds. No pressure, of course, just an invitation to join our small community of nighttime wanderers. So, settle back, maybe find a comfortable position, and let your thoughts drift to the pace of celestial mechanics. We're going to talk about visitors, messengers, and the strange objects that remind us just how connected we are to the vast spaces between stars. The first time astronomers detected something clearly from another star system passing through our neighborhood, it was October 19th, 2017. A Canadian astronomer named Robert Warwick was working with images from the Pan-STARRS telescope in Hawaii when he noticed something moving that shouldn't have been there. At least, not moving quite like that. As we continue to improve our telescopes and survey systems, we'll likely discover many more of these visitors. Each one will bring new information about the diversity of planetary systems, the processes that eject material into interstellar space, and the long, slow mixing that happens as our galaxy evolves. The object was already heading away from us when we found it. It had actually made its closest approach to the Sun about 40 days earlier, sometime in early September, when no one was watching. By the time we spotted it, it was already 21 million miles from Earth and picking up speed as it prepared to leave our solar system forever. What made this discovery so remarkable wasn't just that it came from interstellar space. Objects from beyond our solar system had been predicted for decades. What surprised everyone was how strange it appeared once we started studying it more carefully. The astronomers named it Oumuamua, which means something like a messenger from afar, arriving first in Hawaiian. It seemed like an appropriate name for humanity's first confirmed visitor from the stars, but as telescopes around the world turned to observe Oumuamua during the brief weeks it remained visible, it became clear that this messenger was carrying some very puzzling information. For one thing, Oumuamua was shaped unlike anything we'd ever seen before. As it tumbled through space, spinning once every 7 1/3 hours, its brightness varied dramatically. This told astronomers that it was highly elongated, possibly 10 times longer than it was wide. Picture a cosmic cigar, or maybe a thin pancake, tumbling end over end as it sailed through our solar system. But shape wasn't the only unusual thing about our visitor. Oumuamua was also accelerating slightly as it moved away from the sun, as if something was giving it a gentle push. This kind of acceleration usually happens when comets heat up and release jets of gas and dust. The problem was, Oumuamua didn't look like a comet. It had no visible tail, no glowing coma of gas and dust around it. It appeared completely inert, like a dark reddish chunk of rock, Scientists began to wonder what could cause this mysterious acceleration. Was Oumuamua outgassing after all, but so subtly that we couldn't detect it? Was it being pushed by solar radiation pressure, or was there something else going on entirely? Something we hadn't considered. The mystery deepened as researchers tried to determine what Oumuamua was made of. Recent studies suggest it might have been composed largely of nitrogen ice, similar to what we find on the surface of Pluto. If this is true, then Oumuamua might actually be a fragment from an icy world orbiting another star, a piece of what researchers are calling an exopluto that was somehow ejected from its home system and sent wandering through the galaxy. This possibility is both fascinating and humbling. It suggests that our solar system isn't unique in having icy dwarf planets on the outer edges. It also means that chunks of these distant worlds are constantly moving through space, occasionally passing close enough to other stars for a brief visit. We had to say goodbye to Oumuamua relatively quickly. By January of 2018, it had faded beyond the reach of even our most powerful telescopes. But its visit had taught us something important about the space between stars. It's not empty. There are things moving out there, ancient wanderers carrying stories from other solar systems, if only we knew how to read them. The discovery of Oumuamua also taught us to keep watching more carefully. If one interstellar object had found us, there were probably others. We just needed to be ready to spot them. That patience paid off in August of 2019 when astronomers discovered the second confirmed interstellar visitor, a comet called 2I/Borisov. Unlike Oumuamua, Borisov behaved more like what we expected from an interstellar comet. It had a clear tail and coma, and its chemical composition, while different from solar system comets, was at least recognizably comet-like. But the real surprise came much more recently, this past July, when the Atlas Survey Telescope in Chile spotted something new moving through our skies. Initially designated with the temporary name 11 Play 3Z, this object quickly proved to be our third confirmed interstellar visitor. Now officially named 3I/AT-LUS, this latest messenger from the stars is in some ways the most exciting one yet. Unlike Oumuamua, 3I/AT-LUS is clearly an active comet, complete with a growing tail and a glowing coma of gas and dust. And unlike both previous visitors, it's moving incredibly fast, at about 58 kilometers per second relative to the Sun. That's faster than any interstellar object we've seen before. What makes 3I/ATs particularly intriguing is what we're learning about its composition. Early observations from the James Webb Space Telescope suggest that it's unusually rich in carbon dioxide and water, but the exact ratios are different from what we see in our own solar system's comets. This tells us something about the conditions in whatever distant system originally formed this icy wanderer. The comet is currently making its way through the inner part of our solar system, gradually growing brighter and more active as the sun's heat works on its icy surface. Astronomers expect it to reach its closest approach to the sun sometime in late October, giving us several more months to study this visitor from the stars. The discovery of 3 interstellar objects in just 8 years suggests that these cosmic messengers are more common than we originally thought. Space isn't empty. It's filled with wanderers, fragments of other worlds, pieces of distant histories, all moving on their own trajectories through the galaxy. As we continue to improve our telescopes and survey systems, we'll likely discover many more of these visitors. Each one will bring new information about the diversity of planetary systems, the processes that eject material into interstellar space, and the long, slow mixing that happens as our galaxy evolves. But perhaps most importantly, these interstellar visitors remind us that our solar system isn't isolated. We're part of a dynamic, interconnected galaxy where material moves between star systems, where the story of one world can become part of the story of another, given enough time and the right circumstances. As we watch 3I/Atlas continue its journey through our neighborhood, slowly growing brighter and more active, we're witnessing a connection that spans light years and geological time. This small, icy visitor from another star is temporarily sharing our space, allowing us a glimpse into the chemistry and physics of worlds we may never visit in person. In a few more months, 3I/Atlas will round the sun and begin its long journey back toward interstellar space. Like Oumuamua and Borisov before it, it will eventually fade from our telescope's view and return to the darkness between stars. But the information it shared with us will remain, adding to our understanding of the cosmic neighborhood we're all traveling through together. As we continue our journey through space's strangest discoveries, we move from visitors between the stars to the worlds that orbit them. These aren't ordinary planets, like the ones we know in our solar system. These are worlds that challenge everything we thought we understood about how planets form and survive. Picture a planet the size of Jupiter floating through space with the density of cotton candy, or imagine a world darker than coal, absorbing nearly all light that touches it. Think about a gas giant that somehow survived being swallowed by its dying star. These aren't science fiction fantasies. They're real worlds that astronomers have discovered, each one forcing us to reconsider what we think we know about planetary formation. Tonight, we're going to explore these cosmic rule breakers, the planets that shouldn't exist according to our current theories. Yet there they are, quietly orbiting their stars and keeping their secrets. Let's begin with perhaps the most puzzling category of all, planets that are impossibly light and fluffy, worlds that have earned the whimsical nickname super puffs. About 2,400 light years from Earth, in a star system designated Kepler 51, three planets orbit a sun-like star. When astronomers first studied these worlds, they discovered something extraordinary. Despite being nearly the size of Jupiter, each planet has a mass only 3 to 6 times that of Earth. To put this in perspective, our Jupiter has a mass more than 300 times that of Earth. These planets have a density similar to cotton candy. If you could somehow construct a bathtub large enough, they would float on water. Scientists have never seen anything quite like them in our own solar system, and they're struggling to explain how such worlds could exist. The Kepler 51 planets appear to be enveloped in thick atmospheres of hydrogen and helium that extend tens of thousands of kilometers beyond what we'd expect for planets of their mass. It's as if someone took a normal rocky planet and wrapped it in an impossibly thick, puffy blanket of gas. One explanation is that these planets are simply very young. The Kepler 51 system is only about 500 million years old, compared to our 4.5 billion-year-old solar system. The theory suggests that these planets formed far from their star, where water and other substances could freeze into ice. They then migrated inward, like a string of railroad cars moving closer to the station. Now that they're closer to their star, Their low-density atmospheres should gradually evaporate into space over the next few billion years. Models suggest that in a billion years or so, these cotton candy worlds will shrink and become more like the dense planets we're familiar with. We might be catching them during a brief, puffy phase of their existence. But Kepler 51 isn't the only system with these mysterious superpuffs. Astronomers have discovered similar worlds throughout the galaxy, each one raising new questions about planetary formation. There's WASP 107b, a planet that's about 3/4 the size of Jupiter, but only 1/10 its mass. Recent observations from the James Webb Space Telescope revealed something unexpected about its atmosphere. It contains surprisingly little methane, suggesting that the planet's interior must be much hotter and its core much more massive than previously thought. This unexpected heat might come from tidal forces, as WASP 107b follows its slightly elliptical orbit. The gravitational pull from its star stretches and compresses the planet, generating internal heat that keeps its atmosphere puffed up like a heated balloon. Then there's WASP 193b, a world that's 50% larger than Jupiter, but with a density of just 0.059 grams per cubic centimeter. That's essentially the same density as cotton candy. The planet is so insubstantial that scientists have trouble imagining what solid material could have such low density. These superpuff planets challenge our understanding of how gas giants form. Traditional theory suggests that you need a solid core of at least 10 Earth masses to begin attracting enough gas to build a Jupiter-sized planet. But these cotton candy worlds seem to have accomplished the same result with much smaller cores, raising questions about our models of planetary birth. Meanwhile, on the opposite end of the spectrum, we have planets that are breaking the rules in entirely different ways. These are worlds that somehow survived experiences that should have destroyed them completely. Consider a planet called Hola, also known as 8 Ursae Minoris b. This gas giant orbits a red giant star about 520 light years from Earth. The problem is, it shouldn't be there. Red giant stars are what happens when stars like our Sun begin to run out of fuel. They expand dramatically, sometimes growing to hundreds of times their original size. Our own Sun is expected to become a red giant in about 6 billion years, and when it does, it will likely engulf Mercury and Venus, and possibly Earth as well. Hala's star has already gone through its red giant phase and has now entered the next stage of stellar evolution, burning helium in its core. This means the star should have expanded well beyond Hala's current orbit, swallowing the planet completely. Yet there Hala sits, peacefully circling its elderly star as if nothing unusual had happened. Astronomers have two theories about how Hala might have cheated death. One possibility is that its star was actually part of a binary system, two stars orbiting each other. Perhaps Hala originally orbited both stars, and when they merged together, the merger prevented the red giant from expanding as much as it normally would have. The planet survived because its star never grew large enough to engulf it. Another theory suggests that Hala might actually be a very young planet, formed from the debris of the stellar merger itself. In this scenario, Hala would be a newborn world orbiting an ancient star, having formed billions of years after the star itself. Either way, Hala represents what astronomers call a forbidden planet, a world that exists in conditions where planets shouldn't be able to survive. Similar mysteries exist around white dwarf stars, the final stage in the evolution of sun-like stars. After a red giant sheds its outer layers, what remains is an incredibly dense hot core called a white dwarf. Any planets that existed close to the original star should have been destroyed long ago. Yet astronomers have found evidence of a Jupiter-sized planet orbiting a white dwarf called Guru D 0310-688, located just 34 light years from Earth. This planet appears to orbit within what should be the forbidden zone around the white dwarf, closer than any planet should have been able to survive the star's death. The discovery suggests that planetary systems are more resilient than we thought, or that planets can form or migrate into these forbidden regions after their star's violent transformation. Either possibility forces us to rethink what we know about planetary survival and formation, but perhaps the most visually striking rule breakers are planets that challenge our expectations in completely different ways. These are worlds that absorb almost all light that touches them, making them darker than coal or black paint. Tres 2b, located about 750 light years away, holds the record as the darkest known planet. It reflects less than 1% of the light that hits it, making it darker than charcoal or black acrylic paint. The planet is so dark that if you could somehow shine a flashlight on it, almost none of that light would bounce back to your eyes. This darkness is particularly puzzling because Tres 2b is a hot Jupiter orbiting very close to its star. The intense radiation from the nearby star heats the planet to over 1000 degrees Celsius, hot enough that the planet actually glows with a faint red light like a burning ember. But even this internal glow is barely detectable. The planet's extreme darkness might be caused by light-absorbing chemicals in its atmosphere, such as vaporized sodium and potassium, or gaseous titanium oxide. But none of these substances can fully explain why the world is as dark as it is. There's likely some chemical or process at work that we haven't identified yet. Tres 2b isn't alone in its darkness, and the Zamors have found other remarkably dark worlds, including WASP 104, which absorbs between 97 and 99% of all light that hits it. Like Tres 2b, it probably glows with its own heat, perhaps appearing dark purple like a bruise or red like dying embers. But from our perspective, hundreds of light years away, we can only see its profound darkness. These ultra-dark planets remind us that worlds can exist in conditions far more extreme than anything in our solar system. They represent entirely different categories of planetary atmospheres and surface conditions that we're only beginning to understand. Then there are planets that break the rules about orbital mechanics. In our solar system, all planets orbit the sun in the same direction the sun rotates. This is what we'd expect from planets that formed from a rotating disk of gas and dust around a young star. But some exoplanets orbit their stars backwards, in what astronomers call retrograde motion. Planets like WASP 17b and Kepler 2b travel around their stars in the opposite direction from their star's rotation. This backward motion suggests that these planets didn't form where we find them today, but were instead thrown into their current orbits by gravitational interactions with other planets or passing stars. The existence of these backward orbiting worlds tells us that planetary systems can be much more chaotic and dynamic than our orderly solar system might suggest. Planets can be pushed around, their orbits flipped and twisted by the complex gravitational dance of multiple worlds, sharing the same star. Perhaps most puzzling are the hot Jupiters themselves, gas giants that orbit incredibly close to their stars. Some of these worlds complete an orbit in less than a day, whipping around their stars at speeds that seem to defy logic. HD 800606b, for example, follows an extremely elliptical orbit that takes it incredibly close to its star before swinging back out to greater distances, like a comet made of gas and rock the size of Jupiter. These hot Jupiters couldn't have formed where we find them. It's simply too hot, and there isn't enough material close to stars to build such massive worlds. They must have formed much farther out and then migrated inward, but the exact mechanisms behind this migration are still being debated. Some scientists think these planets spiraled inward through interactions with the gas disk from which they formed. Others believe they were pushed into eccentric orbits by gravitational interactions with other planets, then gradually settled into tight circular orbits through tidal forces. Recent observations suggest that this migration process might take much longer than previously thought. HD 80606 by appears to be caught in the act of migrating inward, giving astronomers a chance to study this process in real time, or at least in astronomical real time, which unfolds over millions of years. What makes all these rule-breaking planets particularly fascinating is that they exist at all. Each discovery forces astronomers to expand their theories about planetary formation and evolution. Every cotton candy planet, every forbidden world, every backward orbiting giant adds another piece to the puzzle of how planets can form and survive in conditions we never imagined possible. These discoveries also remind us that our solar system, with its orderly arrangement of rocky inner planets and gas giants in the outer reaches, might not be as typical as we once thought. The universe appears to be filled with planetary systems of incredible diversity, from cotton candy worlds to coal black giants to planets that dance backward around their stars. As our telescopes become more powerful and our detection methods more sophisticated, we continue to find new categories of impossible planets. Each discovery expands our understanding of what's possible in the universe and challenges us to think more creatively about the processes that shape worlds. These planetary misfits are more than just cosmic curiosities. They're laboratories for testing our theories about physics, chemistry, and planetary formation. They show us conditions and processes that we can't replicate on Earth, giving us glimpses into the incredible diversity of environments that exist throughout the galaxy. Each impossible planet teaches us something new about the fundamental processes that govern the birth and life of worlds. We're going to talk about something that astronomers believe they may have witnessed for the very first time: the birth of a supermassive black hole. This discovery comes from a place so distant that its light has been traveling toward us for over 8 billion years. We're seeing events that happened when our universe was less than half its current age, long before our solar system even existed. And what we're seeing there might change our understanding of how the most massive objects in the universe come to be. The story begins with two astronomers, Peter van Dokkum from Yale University and Gabriel Brammer from the University of Copenhagen, who were quietly searching through images from the James Webb Space Telescope's vast archive. They were looking for cosmic oddities, the kind of unusual objects that might teach us something new about how the universe works. What they found was unlike anything they had seen before. It was a galaxy that appeared to be shaped like the infinity symbol, a perfect figure eight, glowing softly against the darkness of deep space. They decided to call it the Infinity Galaxy, and as they studied it more closely, they realized they might be looking at something extraordinary. The Infinity Galaxy is actually two spiral galaxies caught in the act of colliding. When galaxies merge, it's usually a slow, graceful dance that takes hundreds of millions of years to complete. But in this case, the two galaxies appear to have collided nearly head on, creating something quite dramatic and rare. Each half of the infinity symbol is one of the original galaxies, now surrounded by brilliant rings of stars that were flung outward by the tremendous forces of the collision. These collisional rings give the system its distinctive figure eight appearance, like ripples spreading outward from two stones dropped simultaneously into a still pond. But the shape, as beautiful as it is, wasn't the most surprising thing about the Infinity Galaxy. What caught the astronomers' attention was something glowing brightly right in the center, right between the two colliding galaxies. It was clearly a supermassive black hole, actively feeding on surrounding material, but it wasn't where a supermassive black hole should be. Normally, supermassive black holes live at the centers of galaxies, nestled safely in their cores, where they help hold the galaxy together through their immense gravitational pull. But this black hole was floating in the space between the two galaxies, embedded in a vast cloud of hot ionized gas. Everything is unusual about this galaxy, Van Dalkum explained. Not only does it look very strange, but it also has this supermassive black hole that's pulling a lot of material in. The biggest surprise of all was that the black hole was not located inside either of the two nuclei, but in the middle. We asked ourselves, how can we make sense of this? The question led the researchers to consider something that had been theoretical until now, the possibility that they were witnessing the birth of a supermassive black hole through a process called direct collapse. To understand why this might be significant, we need to talk about one of astronomy's biggest puzzles. Supermassive black holes are found at the centers of virtually every large galaxy, including our own Milky Way. These objects can weigh millions or even billions of times more than our Sun. But how did they get so big? There are two main theories about how supermassive black holes form. The first is called the light seeds model. In this scenario, black holes start small, formed from the collapsed cores of the first massive stars in the universe. Over time, these stellar mass black holes merge with other black holes and continue growing by feeding on surrounding material until they eventually become supermassive. The problem with this theory is time. The merger process is slow, and astronomers have discovered supermassive black holes that existed when the universe was very young, possibly too young for the light seeds process to have created such massive objects. The second theory is called heavy seeds. In this model, supermassive black holes form directly from the collapse of enormous clouds of primordial gas, skipping the stellar phase entirely. Instead of starting with a black hole that weighs as much as a few stars, you immediately get one that weighs hundreds of thousands or even millions of times more than our Sun. The challenge with the heavy seeds theory is that gas clouds naturally want to form stars as they collapse, not black holes. To form a black hole directly, you need very specific conditions that prevent star formation and allow the entire cloud to collapse all at once. These conditions were thought to have existed only in the very early universe, making direct collapse black holes essentially impossible to observe. But the infinity galaxy might be showing us that direct collapse can happen under the right circumstances, even in the more recent universe. Here's what the researchers think happened. About 50 million years ago, two large spiral galaxies began their final approach toward each other. Unlike the slow, gentle mergers we usually see, these galaxies collided nearly head on at tremendous speed. The collision created shockwaves that rippled through both galaxies, compressing and heating the gas between them. This compressed gas formed a dense, turbulent cloud right at the collision site, suspended between the two galaxy cores like a cosmic bridge. Normally, such a dense cloud would quickly cool down and begin forming stars, but the violence of the collision, combined with the intense radiation from the newly disturbed galaxy cores, kept the gas hot and turbulent. Unable to cool and fragment into stars, the entire cloud became unstable and collapsed directly into a black hole. The black hole that formed was already quite massive, perhaps several 100,000 times the mass of our Sun, and because it found itself in the middle of a rich feeding ground, surrounded by shocked and compressed gas from the collision, it began growing immediately. What we see today, 8 billion years later, is a supermassive black hole that weighs about 1 million times as much as our Sun, still actively feeding on the gas cloud that gave birth to it. The black hole is surrounded by hydrogen gas that glows brightly as it gets heated by the intense radiation from material falling into the black hole. To confirm their theory, Van Dockum and his colleagues requested additional observation time with the James Webb Space Telescope. They wanted to measure the velocity of the gas around the black hole and compare it to the velocity of gas in the rest of the infinity galaxy. If the black hole had wandered in from somewhere else, its motion would be different from the motion of the surrounding galaxy. But if it had formed right there in the collision, its velocity should match that of the local gas. The additional observations provided exactly the confirmation they were looking for. The black hole's velocity matched that of the surrounding gas perfectly, strongly suggesting that it had indeed formed right there in the cloud of shocked gas between the colliding galaxies. But the follow-up observations revealed another surprise. Each of the two original galaxies also contains its own supermassive black hole in its nucleus, meaning the infinity galaxy system actually hosts three supermassive black holes in total. It's a cosmic family portrait of black holes, two ancient ones that formed in the normal way at the centers of their galaxies, and one newborn that came into being through direct collapse in the space between them. The discovery of what appears to be a direct collapse black hole has implications far beyond this single system. It suggests that the heavy seeds pathway for supermassive black hole formation is not just theoretical, but actually happens in nature. This could help explain one of the most puzzling discoveries of the James Webb Space Telescope, the existence of extremely massive black holes in the very early universe, less than 1 billion years after the Big Bang. These ancient giants are so massive that it's difficult to understand how they could have grown so large so quickly through the traditional light seeds process. But if supermassive black holes can form directly from collapsing gas clouds, then they start life already weighing hundreds of thousands or millions of solar masses. From there, it's much easier to understand how they could grow to billions of solar masses within the first billion years of cosmic history. The infinity galaxy also gives us a glimpse into the violent and chaotic nature of the early universe. When the cosmos was young and galaxies were still forming, collisions and mergers were much more common than they are today. The intense conditions created by these cosmic crashes might have been perfect for direct collapse black hole formation. In those early times, gas clouds were more pristine, containing mostly hydrogen and helium without the heavier elements that help gas cool and form stars. The combination of frequent galaxy collisions and primitive gas composition might have made direct collapse black holes relatively common in the young universe. Today, such events are much rarer. Galaxies are more spread out, collisions are less frequent, and gas clouds contain heavier elements that make star formation more likely than black hole formation. The infinity galaxy might represent a rare glimpse of processes that were once commonplace but are now almost extinct. The researchers are careful to note that they can't definitively say they found a direct collapse black hole. Other explanations are possible, though less likely. The black hole could be a runaway that was ejected from one of the galaxies and just happened to be passing through when we observed it. Or it could be the central black hole of a third very faint galaxy that we can't see directly. But the evidence for direct collapse is compelling. The black hole's position, exactly between the two galaxy nuclei, its velocity matching that of the surrounding gas, and its location within a cloud of shocked, compressed material all point to formation right there at the collision site. As Van Dockum puts it, this is as close to a smoking gun as we're likely ever going to get. The infinity galaxy represents more than just an unusual cosmic configuration. It's a window into fundamental processes of black hole formation, a laboratory where we can study conditions that existed throughout the early universe, and potentially the first direct observation of one of the most important events in cosmic evolution, the birth of a supermassive black hole. The fact that we can witness such an event at all is remarkable. Black hole formation usually happens hidden deep within dense clouds of gas and dust, obscured from our view, but the particular geometry of the infinity galaxy collision has created conditions where we can see the process clearly, like watching the birth of a star through a gap in a dust cloud. As follow-up observations continue and computer simulations become more sophisticated, we'll learn more about the exact conditions that led to this direct collapse event. Each new piece of information helps us understand not just this single system, but the broader processes that shaped the early universe and continue to govern the formation of the most massive objects in the cosmos. The infinity galaxy reminds us that the universe is still full of surprises, still capable of showing us phenomena we've never seen before. It's a testament to the value of patient observation and careful analysis, and to the incredible power of our most advanced telescopes to reveal the hidden workings of the cosmos. In the end, this cosmic figure 8, floating in space, 8 billion light years away, might hold the key to understanding how supermassive black holes come to be. It's a beautiful reminder that sometimes the most profound discoveries come from simply looking carefully at the unexpected and asking the right questions about what we see. Moving forward in our journey through space's greatest mysteries, we now travel to the very edge of our solar system. Here, in the vast emptiness, billions of miles from the sun, two aging spacecraft have made discoveries that challenge everything we thought we knew about where our solar system ends and interstellar space begins. The story begins with two machines launched nearly 50 years ago, when most of today's listeners weren't even born. Voyager 1 and Voyager 2 left Earth in 1977 with a mission to explore the outer planets. Nobody expected them to keep working for half a century. Nobody imagined they would travel so far from home that they would cross the boundary between our solar system and the space between the stars. But that's exactly what happened, and what they found out there was nothing like what scientists expected. The boundary they crossed is called the heliopause. Think of it as the edge of a vast bubble blown by our sun, a protective shield that surrounds all the planets and extends far beyond even Pluto's orbit. This bubble is created by the solar wind, a constant stream of charged particles flowing away from the sun in all directions. For billions of kilometers, these solar particles flow unimpeded through space, but eventually they encounter something else: the interstellar medium, the cold, ancient material that fills the space between stars. When these two forces meet, they create a boundary, a cosmic shoreline where our sun's influence ends and the vast ocean of interstellar space begins. Voyager 1 was the first human made object to cross this boundary on August 25th, 2012. 6 years later, Voyager 2 followed. They crossed at different locations, but the measurements they sent back revealed something extraordinary and unexpected. At the heliopause, both spacecraft encountered what scientists have come to call a wall of fire. But this isn't fire in any sense we would recognize. There are no flames in the vacuum of space. Instead, it's a region where the temperature of charged particles suddenly spikes to 30,000 or even 50,000 degrees Celsius. To put this in perspective, the surface of the sun is about 5,500 degrees. The region these spacecraft encountered is nearly 10 times hotter. Yet this isn't thermal heat as we understand it. It's the kinetic energy of particles being compressed and accelerated as two cosmic rivers meet and collide. Scientists think this extreme heating happens because of magnetic reconnection, a process where magnetic field lines from our sun merge with the magnetic fields of interstellar space. When these field lines snap and reconnect, they release enormous amounts of energy, heating the surrounding plasma to these incredible temperatures. What makes this discovery even more intriguing is that both spacecraft survived this encounter completely unharmed. The extremely high particle energies exist in a medium so thin that there simply isn't enough material to transfer significant heat to the spacecraft. It's like walking through a cloud of individual hot needles scattered so far apart that you never actually touch one. But the wall of fire isn't the only mystery the Voyagers encountered at the edge of our solar system. Perhaps even more puzzling is what they discovered about magnetic fields. Before the Voyagers reached interstellar space, scientists expected the magnetic environment outside our solar system to be completely different from the one inside. The magnetic field carried by the solar wind should have been pointing in one direction, while the magnetic field in interstellar space should have been pointing in a completely different direction. But that's not what happened. When Voyager 1 crossed the heliopause, it found that the magnetic fields on both sides of the boundary were remarkably similar, almost perfectly aligned. Scientists wondered if this might be a coincidence, a stroke of luck that Voyager 1 just happened to cross at a place where the fields accidentally lined up. Then Voyager 2 crossed the boundary at a completely different location, billions of kilometers away from where Voyager 1 had crossed, and it found exactly the same thing. The magnetic fields inside and outside the heliopause were aligned in the same direction. This discovery has profound implications for our understanding of how our solar system connects to the galaxy around it. It suggests that our sun's magnetic influence may extend much farther than we thought, subtly shaping the interstellar environment around our solar system. Or it might mean that the magnetic field in our local region of the galaxy has an organized structure that we don't yet understand. The aligned magnetic fields also raise questions about the nature of the heliopause itself. Instead of being a sharp boundary between two completely different environments, it might be more like a permeable membrane, a region where solar and galactic influences gradually blend together. This idea is supported by another strange discovery the Voyagers made. The heliopause appears to be leaking. Both spacecraft detected particles from the opposite side of the boundary, mixing across what should have been an impermeable barrier. Voyager 1 found interstellar particles streaming into the solar system, while Voyager 2 detected solar particles lingering in interstellar space long after it had crossed the boundary. This suggests that the heliopause isn't the solid wall scientists once imagined, but rather a complex, dynamic interface where material can flow both ways. The shape of this boundary is also far more complex than anyone expected. Early models suggested that the heliopause would be relatively smooth and stable, like a soap bubble holding its shape as it drifts through the air. But data from the Interstellar Boundary Explorer, or IBEX, satellite has revealed that the boundary is constantly shifting and rippling. These ripples can be enormous, extending for tens of astronomical units. That's hundreds of millions of kilometers of distortion, as if the boundary were made of a flexible fabric being pushed and pulled by unseen forces. The cause of these ripples remains mysterious, though scientists suspect they might be related to changes in solar activity or interactions with the local interstellar environment. Perhaps most surprisingly, the Voyagers discovered that the heliopause responds to events happening near the Sun, coronal mass ejections, powerful explosions that blast huge amounts of solar plasma into space, can create shock waves that propagate all the way to the edge of the solar system and beyond. When these shock waves reach the heliopause, they can temporarily push the boundary outward, like a balloon being inflated by a sudden puff of air. The Voyagers have detected these shock waves crossing into interstellar space, carrying with them information about solar activity that occurred years earlier. This discovery reveals that our sun's influence extends far beyond the heliopause, affecting conditions in interstellar space itself. It also suggests that similar processes might be happening around other stars, with shock waves from stellar explosions rippling through the galaxy and potentially affecting the formation and evolution of planetary systems. The temperature and density measurements made by the Voyagers have also challenged existing theories. Scientists expected that as the solar wind slowed down and compressed at the heliopause, its temperature and density would increase dramatically. While this heating did occur, the measured values were about 10 times lower than theoretical predictions suggested they should be. This discrepancy points to gaps in our understanding of plasma physics at these scales. There may be processes at work that our current models don't account for, mechanisms that transport energy away from the boundary region or that cool the plasma more efficiently than we realized. Another puzzle involves the cosmic ray environment. The heliopause acts as a partial shield against galactic cosmic rays, high energy particles accelerated by exploding stars and other violent cosmic events. The Voyagers confirmed that crossing the boundary leads to a significant increase in cosmic ray exposure, as expected. But the cosmic ray environment in interstellar space turned out to be more complex than anticipated. The particles don't just increase uniformly, their energy spectrum and directional distribution provide clues about conditions in the local interstellar medium and the history of cosmic ray acceleration in our region of the galaxy. These measurements have implications for understanding space weather and its effects on both robotic missions and eventual human exploration of the outer solar system. They also provide information about the galactic environment that our solar system has encountered during its journey around the Milky Way. The Voyager discoveries have revealed that the boundary between our solar system and interstellar space is not a simple, well defined edge, but rather a complex transition zone filled with unexpected phenomena. The wall of fire, the aligned magnetic fields, the leaking boundary, and the dynamic ripples all point to a heliopause that is far more active and interconnected than anyone imagined. These findings are forcing scientists to rethink fundamental questions about how our solar system interacts with the galaxy around it. They suggest that the boundaries between stellar systems and interstellar space are permeable and dynamic, allowing for the exchange of matter, energy, and magnetic fields across vast distances. As the Voyager spacecraft continue their journey into interstellar space, they keep sending back data that challenges our understanding of these cosmic boundaries. Each measurement provides new insights into the nature of the space between stars and the complex processes that govern the interaction between stellar and galactic environments. The signals from the edge of our solar system remind us that even the most fundamental boundaries in space are more complex and mysterious than we initially realized. They show us that our solar system is not an isolated island floating in an empty void, but rather an active participant in the dynamic ecology of our galaxy. These discoveries also demonstrate the incredible value of long-term space missions. The Voyager spacecraft, launched when disco was popular and personal computers didn't exist, continue to make groundbreaking discoveries nearly 5 decades later. They remind us that some of the most important scientific questions require patience, persistence, and the courage to send our instruments into the unknown. As both Voyagers continue their slow journey into the depths of interstellar space, they carry with them the hopes and curiosity of the species that built them. They are our furthest ambassadors, still whispering back to us across the vast darkness, still teaching us about the nature of the cosmic neighborhood we call home. Building on this understanding of unexpected phenomena throughout the cosmos, we now turn to a discovery that happened entirely by accident. Sometimes the most profound scientific insights come not from carefully planned observations, but from stumbling upon something that shouldn't be there at all. In 2020, a citizen scientist named Dan Caselden was doing what he often did in his spare time. He was looking through images from NASA's NEOWISE telescope, participating in a project called Backyard Worlds, Planet 9. The project invites people from around the world to help search for new objects in our cosmic neighborhood, particularly brown dwarfs, and possibly even a ninth planet lurking in the outer reaches of our solar system. Caselden wasn't looking for anything in particular that night. He was simply scrolling through images, letting his eyes wander across the star fields, when something caught his attention. There was an object moving rapidly across the sky, something that looked strange and out of place. It was moving too fast to be a distant star, but it didn't look quite like anything he'd seen before. The discovery was so unexpected that the research team decided to give this object a fitting nickname, They called it the accident. At first glance, the accident appeared to be just another brown dwarf, one of those mysterious objects that exist in the twilight zone between planets and stars. Brown dwarfs are sometimes called failed stars because they're too small to sustain the nuclear fusion reactions that make stars shine, but too large to be considered planets. They're cosmic middle children, not quite fitting into either category. But as astronomers began studying the accident more carefully, they realized this particular brown dwarf was far from ordinary. It had a perplexing mix of physical features that didn't make sense together. Some characteristics suggested it was very young, while others indicated extreme age. It was as if someone had taken parts from completely different cosmic objects and somehow assembled them into a single contradictory whole. The mystery deepened when researchers tried to classify the accident using standard astronomical methods. Every classification system they used gave different results. The object seemed to exist in a category all its own, defying the usual ways astronomers organize and understand brown dwarfs. Because the accident was so unusual and so faint, researchers needed NASA's most powerful space observatory, the James Webb Space Telescope, to study its atmosphere in detail. What they found there surprised them even more than the object's strange physical properties. Among the various molecules Webb detected in the accident's atmosphere, one stood out as completely unprecedented. The astronomers found clear evidence of a simple silicon molecule called silane. This might not sound particularly exciting, but it was actually a momentous discovery. It was the first time silane had ever been detected in the atmosphere of any celestial body anywhere in the universe. The significance of this discovery goes far beyond just finding a new molecule in space. Scientists have long expected to find silane in the atmospheres of gas giant planets like Jupiter and Saturn, but they've never been able to detect it. This absence has been one of the puzzling mysteries of planetary science. Silicon is one of the most common elements in the universe. It's everywhere, from rocky planets to interstellar dust. Logic suggests it should be abundant in gas giant atmospheres too, yet spacecraft that have studied Jupiter and Saturn up close have found barely any trace of silicon-containing molecules in their upper atmospheres. The discovery of silane in the accident finally provided the answer to this long-standing puzzle. The key lies in understanding what happens to silicon when other elements are present in large quantities. In most atmospheric environments, silicon doesn't remain free to form simple molecules like silane. Instead, it binds with oxygen to create complex compounds like silicates, the same materials that make up rocks and sand here on Earth. In gas giant atmospheres, these silicon-oxygen compounds form tiny particles that condense into clouds and then sink deep into the atmosphere, far below the levels where our instruments can detect them. It's like having flour in a kitchen. If you leave flour on a countertop, you can see it and measure it easily. But if you mix the flour into bread dough and bake it, the individual flour is no longer visible or easily measurable, even though it's still there, incorporated into something larger and more complex. The same thing happens with silicon in most gas giant atmospheres. The silicon is there, but it's locked away in clouds that sink so deep into the atmosphere that they become invisible to our instruments. Any silicon that might remain free to form molecules like silane gets used up in this cloud formation process, leaving none available for detection. But the accident is different. This brown dwarf is incredibly old, likely formed between 10 and 13 billion years ago, when the universe was less than a quarter of its current age. At that time, the cosmos was a much simpler place chemically. The universe contained mostly hydrogen and helium, with only trace amounts of heavier elements. The heavier elements that are common today, including oxygen, carbon, and nitrogen, are created in the cores of stars over billions of years. When those stars die and explode, they scatter these elements throughout the galaxy, enriching the material from which new stars and planets form. This process takes time, lots of time. When the accident formed all those billions of years ago, there simply wasn't very much oxygen available. Without sufficient oxygen to bind with all the silicon and form clouds, some silicon remained free in the atmosphere. This free silicon could then bond with hydrogen to create silane, the molecule that Webb finally detected. The discovery confirms that silane can indeed form in brown dwarf and planetary atmospheres, just as scientists had predicted. The reason we don't see it in other objects is that oxygen is so abundant in more recently formed atmospheres that it bonds with virtually all available silicon, leaving none to form silane. This finding has profound implications for understanding the atmospheric chemistry of gas giants throughout the galaxy. It suggests that planets forming around older metal-poor stars might have atmospheric compositions quite different from what we observe in our own solar system. These ancient worlds might be rich in silicon compounds that are completely absent from younger planets. The discovery also provides new insights into the chemical evolution of the galaxy itself. By studying objects like the accident, astronomers can learn about the conditions that existed billions of years ago when the universe was young and the first generations of planets were forming. But the accident's contribution to science doesn't stop with silane. The brown dwarf's unusual properties are helping astronomers understand why some objects are so difficult to classify. It appears that the accident formed at a time when the galaxy's chemical composition was in transition, giving it characteristics that don't fit neatly into modern classification schemes. The object is also providing clues about brown dwarf formation itself. Scientists are still debating exactly how these failed stars come to exist. Some form like stars do, from the gravitational collapse of gas clouds. Others might form more like planets, building up gradually from smaller pieces. The accident's strange mix of properties suggests it might represent a transitional case formed under conditions that no longer exist in today's galaxy. The research team, led by Jackie Faraday from the American Museum of Natural History, describes the accident as an extreme object that helps illuminate the properties of more typical brown dwarfs and gas giants. Sometimes they explain it's the outliers that teach us the most about the normal cases. This discovery also highlights the value of citizen science projects like Backyard Worlds, Planet 9. Without Dan Castleton's keen eye and willingness to spend his free time examining telescope images, the accident might never have been discovered. It's a reminder that important scientific discoveries can come from anyone, anywhere, who takes the time to look carefully at the cosmos. The fact that such an unusual object existed undetected for so long also suggests that there are likely many more strange worlds waiting to be discovered. Each new brown dwarf, each peculiar atmospheric composition, each unexpected chemical signature adds to our understanding of how planetary atmospheres work and evolve. As Webb continues to study the accident and other unusual objects, astronomers expect to uncover more surprises about atmospheric chemistry. Each discovery helps refine our models of how gas giant atmospheres behave under different conditions and at different stages of cosmic history. The accident reminds us that the universe is full of natural laboratories, places where cosmic chemistry experiments have been running for billions of years. By studying these distant worlds, we can learn about processes and conditions that we could never replicate on Earth, expanding our understanding of how planets and atmospheres work throughout the galaxy. In the end, this accidental discovery of an ancient brown dwarf has helped solve mysteries about our own gas giant planets, while opening up new questions about atmospheric evolution and planetary formation in the early universe. It's a perfect example of how serendipitous discoveries in astronomy often lead to the most profound insights about our cosmic neighborhood. As we continue our exploration of cosmic mysteries, we encounter something that seems to defy the natural order of the universe. We're going to talk about black holes that are spinning in the wrong direction, cosmic giants that have somehow been knocked over onto their sides like celestial bowling pins. This story begins not with a dramatic new observation, but with something much quieter and more methodical. It's about the patient work of scientists who spend their time looking through old data, searching for patterns that previous generations of astronomers might have missed. In the archives of NASA's Chandra X-ray Observatory, there were decades of observations from a galaxy called NGC 5084. This galaxy, located about 80 million light years away in the constellation Virgo, had been photographed and studied many times over the years. It appeared to be a fairly typical lenticular galaxy, one of those lens-shaped systems that exist somewhere between spiral galaxies, like our Milky Way, and the more amorphous elliptical galaxies. But Dr. Alejandro Serrano Borlaf, a researcher at NASA's Ames Research Center, suspected there might be more to NGC 5084 than met the eye. He was testing a new image analysis technique his team had developed, something they playfully called SONES, which stands for Selective Amplification of Ultra-Noisy Astronomical Signal. The technique is designed to tease out faint X-ray emissions that might be hidden in the noise of older observations. It's like having a special filter that can reveal whispers of light that were always there, but too quiet to be heard above the cosmic background chatter. When Borlaf applied SONAS to the archival data from NGC 5084, he discovered something that made him stop and look again. There were 4 long plumes of hot glowing plasma stretching away from the galaxy's center, forming a perfect X shape against the darkness of space. This was already unusual. When astronomers see X-ray emissions from massive galaxies, they typically expect to find them spread out relatively evenly, creating a roughly spherical glow around the galactic center. The sight of such organized, concentrated beams of high-energy light suggested that something dramatic had happened in this galaxy's recent past. 2 of the plasma plumes extended above and below the plane of the galaxy, which is not entirely uncommon in some types of galaxies. But the second pair, stretching through the galactic plane and crossing the first pair to create that X shape, was something the team had never seen before. Detecting 2 pairs of X-ray plumes in one galaxy is exceptional, explains Pamela Markham, an astrophysicist at Ames Research Center, who worked on the discovery. The combination of their unusual cross-shaped structure gives us unique insights into this galaxy's history. The discovery was so strange that it immediately sent the research team scrambling to confirm their findings. They began scouring the archives of other telescopes and requesting new observations from ground-based observatories. They needed to understand what could create such an unusual pattern. Additional data from the Hubble Space Telescope and the Atacama Large Millimeter Array in Chile revealed something even more intriguing. There was a small dusty disk at the very heart of NGC 5084, material swirling around what could only be a supermassive black hole. But this disk had a problem. It was tilted 90 degrees relative to the rest of the galaxy. The black hole and its surrounding material were essentially lying on their sides, spinning in a direction that was completely perpendicular to the galaxy's overall rotation. It was like seeing a crime scene with multiple types of light, Borlaug explained. Putting all the pictures together revealed that NGC 5084 has changed a lot in its recent past. This sideways orientation is profoundly unusual in the cosmic scheme of things. Supermassive black holes typically form at the centers of galaxies and grow up with them over billions of years. During this long coevolution, the black hole's rotation should naturally align with the galaxy's overall spin. It's like a record spinning on a turntable, and records to be moving in the same plane and the same direction. But sometimes, something goes wrong. Sometimes an event so violent occurs that it can literally tip a supermassive black hole over onto its side, changing its orientation relative to its host galaxy. The most likely explanation for what happened to NGC 5084 is a galactic collision billions of years ago. This galaxy probably encountered another large galaxy, and the two systems began a slow gravitational dance that eventually culminated in a merger. During such collisions, enormous tidal forces distort and reshape both galaxies. Stars are flung into new orbits, gas clouds are compressed and heated, and the supermassive black holes at the centers of both galaxies begin spiraling toward each other. This process creates shock waves and plasma outflows that can persist for hundreds of millions of years after the initial collision. The violence of this merger could have generated the chimney-like structures that extend above and below NGC 5084's plane. Meanwhile, the gravitational chaos of having two massive black holes in close proximity could have torqued and twisted the central regions of the galaxy, eventually flipping the surviving black hole onto its side. The cross-shaped pattern of X-ray emissions we see today might be the signature of this ancient violence, a cosmic scar that has persisted long after the collision ended. The fact that we can still see these structures suggests that the merger happened relatively recently in cosmic terms, perhaps within the last billion years or so. This discovery has broader implications for our understanding of how galaxies and their central black holes evolve together. It suggests that the relationship between a galaxy and its supermassive black hole isn't always as harmonious as we once thought. Major disturbances, like galaxy mergers, can disrupt this relationship and create configurations that persist for cosmic ages. The sideways black hole in NGC 5084 isn't entirely unique. Our own galaxy's supermassive black hole, Sagittarius A, also shows signs of being misaligned with the Milky Way's overall rotation, though not as dramatically as the one in NGC 5084. Recent studies suggest that Sagittarius A might also have experienced a major collision in the distant past, one that altered its spin and left it rotating at a slight angle to our galaxy's disk. These discoveries are part of a growing recognition that supermassive black holes can have complex, sometimes violent histories that leave lasting marks on their properties. They remind us that even these cosmic giants, objects so massive that they anchor entire galaxies, are not immune to the chaotic forces that shape the universe. The case of NGC 5084 also demonstrates the incredible value of archival data. The observations that revealed this sideways black hole had been sitting in Chandra's archives for years, waiting for the right analytical technique to unlock their secrets. It's a reminder that sometimes the most important discoveries are hiding in plain sight, in data we've already collected but haven't yet learned how to properly examine. As we develop more sophisticated methods for analyzing astronomical data, we're likely to find more examples of these tilted black holes and other unusual configurations. Each discovery helps us piece together the violent and dynamic history of galaxy formation and evolution. The research team describes their work as cosmic detective work, and that's exactly what it is. They're examining a crime scene billions of years after the fact, using multiple types of evidence to reconstruct what happened during one of the most violent events in the universe, the collision and merger of two massive galaxies. The sideways black hole in NGC 5084 stands as a testament to the incredible forces at work in our universe. It reminds us that even the most fundamental structures in the cosmos, the relationship between a galaxy and its central black hole, can be disrupted and reshaped by the grand dance of celestial mechanics. As we continue to develop new techniques for analyzing old data and making new observations, we're sure to discover more of these cosmic anomalies. Each one teaches us something new about the complex, often violent processes that have shaped the universe we see today. The story of NGC 5084 also shows us the importance of looking at familiar objects in new ways. This galaxy had been studied for decades, but it took a fresh analytical approach to reveal its hidden secret. It's a reminder that the universe is full of mysteries waiting to be uncovered, even in places we think we already understand. In the end, this sideways black hole represents more than just an astronomical curiosity. It's a window into the dynamic, ever-changing nature of the cosmos, a reminder that even the largest structures in the universe are subject to forces that can reshape them in fundamental ways. It tells us that the universe is not a static, orderly place, but rather a dynamic arena where cosmic violence can leave lasting marks that persist for billions of years, waiting patiently for us to discover them and piece together their stories. In parallel to this understanding of unusual cosmic structures, we encounter something perhaps even more mysterious. Imagine if you could somehow photograph the entire cosmos with a time exposure camera, leaving the shutter open for years at a time. Most of what you'd capture would be the steady, gentle glow of stars and galaxies, unchanged from day to day, year to year. But occasionally, scattered across your cosmic photograph, you'd see brilliant white streaks, like cosmic lightning frozen in time. These are the universe's flashbulbs, phenomena so energetic that they can release in milliseconds more power than our sun will emit in days, months, or even years. They appear without warning, blaze with impossible brightness, and then vanish, often never to be seen again. The story of how we discovered these cosmic flashbulbs begins in the most ordinary way possible. In 2007, a graduate student named David Narkovic was doing what graduate students often do. He was looking through old data, searching for signals that previous researchers might have overlooked. Narkovic was working with his advisor, Duncan Lorimer, examining archived observations from the Parkes radio telescope in Australia. They were looking for pulsars, the lighthouse like beams of radio waves emitted by rapidly spinning neutron stars. It was methodical work, the kind of patient data analysis that forms the backbone of astronomy. Then, buried in observations from 2001, they found something that shouldn't have been there. It was a burst of radio waves, so brief and so intense that it initially seemed like it must be some kind of instrumental error. The signal lasted just 5 milliseconds, but in that tiny fraction of a second, it emitted as much energy in radio waves as the sun produces in an entire day. The burst appeared to have traveled from far outside our galaxy, somewhere in the distant universe. But how could anything so distant produce a signal powerful enough to be detected across billions of light years of space? At first, Lorimer and Narkovic wondered if they were seeing some kind of terrestrial interference, perhaps a microwave oven or a cell phone tower creating a false signal, but the properties of the burst didn't match any known source of radio interference. The signal showed the telltale signs of having traveled through the cosmic medium, picking up a slight delay that occurs when radio waves pass through the thin gas that fills intergalactic space. They had discovered the first fast radio burst, or FRB. The scientific community initially met their discovery with skepticism. A single unexplained burst, buried in old data, wasn't enough to convince most astronomers that a new cosmic phenomenon had been found. But then more FRBs started appearing as radio telescopes became more sensitive and automated search systems more sophisticated. Astronomers began finding these mysterious signals regularly. Today, we detect several thousand fast radio bursts every year, flashing across the sky from all directions. Each FRB is a mystery wrapped in an enigma. They last anywhere from fractions of a millisecond to a few seconds at most. They can release as much energy in that brief time as our sun will produce in 3 days, 30 years, or in some extreme cases, centuries. Yet by the time we detect them on Earth, the signal has weakened so much during its journey across cosmic distances that it's weaker than the radio signal from a cell phone on the moon. What makes FRBs even more puzzling is their apparent randomness. Most appear once and are never seen again. They flash from different locations across the sky with no apparent pattern or warning. It's as if the universe is filled with cosmic flashbulbs that fire once and then burn out forever. But some FRBs break this pattern. In 2012, astronomers discovered FRB 121102, a source that defied the rules by repeating instead of a single flash. This object produced burst after burst of radio waves, sometimes separated by days, sometimes by months. The discovery of repeating FRBs opened up new possibilities for study, allowing astronomers to point multiple telescopes at the same patch of sky and wait for the next burst to occur. The repeating sources help solve at least part of the FRB mystery. By precisely measuring the positions of several repeating FRBs, astronomers were able to trace them back to their host galaxies. What they found was both surprising and enlightening. FRBs appeared to come from a wide variety of galactic environments, from quiet, elderly galaxies to active, star forming regions. This diversity of environments suggests that FRBs might not have a single cause. Instead, there could be multiple types of cosmic events capable of producing these intense radio flashes. The most popular explanation involves magnetars, neutron stars, with magnetic fields trillions of times stronger than Earth's magnetic field. When the twisted magnetic field lines around a magnetar suddenly snap and reconnect, they can accelerate charged particles to tremendous speeds, creating an intense burst of radiation. Support for this theory came in 2020 when astronomers detected the first FRB from within our own Milky Way galaxy. The source was a known magnetar, and the burst occurred simultaneously with an X-ray flare from the same object. But magnetars can't explain all FRBs. Some of the most powerful bursts appear to come from environments where magnetars shouldn't exist. This suggests that there are other, possibly more exotic, mechanisms at work in the universe's flashbulb factory. Meanwhile, in the optical part of the spectrum, astronomers have discovered another type of cosmic flashbulb that's equally mysterious and perhaps even more dramatic. These are called luminous fast blue optical transients, or LF-BOTs, and they represent some of the brightest explosions ever seen in the universe. LF-BOTs shine intensely in blue light and evolve with breathtaking speed. Unlike supernovae, which take weeks or months to reach peak brightness and fade, LF-BOTs can brighten and fade within just a few days. They can outshine their entire host galaxies for a brief moment, then disappear almost as quickly as they appeared. The first LF-BOT was discovered in 2018 and was nicknamed the Cow after its official designation at 2018 Cow. Since then, astronomers have found only a handful of additional LF-BOTs, making them even rarer than the rarest types of supernovae. Each new LF-BOT discovery has only deepened the mystery. In 2023, the Hubble Space Telescope spotted an LF-BOT nicknamed the Finch that occurred not within a galaxy, but in the apparently empty space between galaxies. This was completely unexpected, as previous LF-BOTs had always been found in regions where massive stars were forming. But perhaps the strangest LF-BOT ever discovered is one that astronomers have nicknamed the Tasmanian Devil. This cosmic flashbulb, officially designated AT 2022 TSD, broke all the rules about how LF-BOTs are supposed to behave. Like other LF-BOTs, the Tasmanian Devil began with a brilliant initial flash that outshone its host galaxy, but instead of fading quietly into darkness, it continued to produce additional bright flares for months afterward. Over a period of 120 days, astronomers detected at least 14 separate outbursts from the same location, each one lasting only a few minutes, but releasing enormous amounts of energy. No one really knew what to say, explained Anna Hu, the Cornell University astronomer who led the study. We had never seen anything like that before. Something so fast, and the brightness as strong as the original explosion months later. We'd never seen that, period, in astronomy. The repeated flaring of the Tasmanian Devil suggests that whatever causes LF-BOTs might be more complex and long-lasting than anyone had imagined. One possibility is that the initial explosion creates a black hole or neutron star that continues to actively feed on surrounding material, producing the subsequent flares as matter falls into the compact object. This idea fits with a broader pattern that astronomers are beginning to recognize across multiple types of cosmic flashbulbs, whether we're talking about fast radio bursts, gamma ray bursts, or LF bots. Many of the universe's most energetic phenomena seem to involve compact objects like neutron stars and black holes in extreme situations. These objects represent matter compressed to densities so extreme that a teaspoon of material would weigh as much as a mountain. When such objects are formed in stellar explosions, when they collide with each other, or when they suddenly begin feeding on nearby material, the result can be a cosmic flashbulb of almost unimaginable power. But the exact mechanisms remain frustratingly unclear. Each new discovery brings new surprises and new questions. The brightest FRB ever detected, nicknamed RBF for radio brightest flash of all time, was discovered in March 2025. It came from a galaxy 130 million light years away, close enough for detailed study, yet its properties still don't fit neatly into existing theories. What makes these cosmic flashbulbs particularly intriguing is their apparent ubiquity. FRBs are now known to occur thousands of times per day across the entire sky, suggesting that whatever produces them is a common process in the universe. Yet each burst is so brief and so distant that studying them in detail remains incredibly challenging. The situation is like trying to understand lightning by examining individual lightning bolts that last only microseconds and occur hundreds of miles away. You can measure their brightness and duration, but understanding the underlying physical processes requires patience, sophisticated instruments, and more than a little luck. Recent advances in telescope technology and data processing are finally allowing astronomers to make progress on these mysteries. New facilities like the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, can monitor large portions of the sky continuously, catching FRBs in real time and immediately alerting other telescopes to make follow-up observations. These coordinated observations are beginning to reveal the environments where cosmic flashbulbs occur and the aftermath they leave behind. Each piece of new information helps constrain theories about what might cause these extraordinary events. The study of cosmic flashbulbs also highlights one of the most exciting aspects of modern astronomy: the discovery that the universe is far more dynamic and violent than previous generations of astronomers realized. The night sky, which appears peaceful and unchanging to the naked eye, is actually filled with constant activity. Stars explode, black holes devour matter, neutron stars collide, and mysterious processes we don't yet understand produce the brightest flashes of light in the universe. These discoveries remind us that the cosmos is not a static museum display, but a living, evolving system where extreme events occur regularly on scales that dwarf anything we experience on Earth. Every cosmic flashbulb represents a natural laboratory where matter and energy interact under conditions that we could never replicate artificially. As our ability to detect and study these events continues to improve, we're likely to discover even more exotic types of cosmic flashbulbs. Each new category of event will bring fresh mysteries and new opportunities to understand the fundamental processes that govern the universe. The flashbulbs remind us that some of the most important events in the cosmos happen not over millions or billions of years, but in fractions of seconds. In those brief moments, the universe reveals processes and energies that shape the evolution of galaxies, the distribution of heavy elements, and possibly even the conditions necessary for life to emerge and flourish. They are reminders that the universe is full of surprises, capable of producing phenomena so extreme and so brief that they challenge our ability to observe and understand them. Yet each flash, each burst, each cosmic flashbulb adds another piece to the puzzle of how the universe works at its most fundamental level. Gradually, as we continue our journey through space's most perplexing discoveries, we arrive at one of the James Webb Space Telescope's most bewildering findings. These aren't dramatic explosions or massive collisions. Instead, they're some of the tiniest, most subtle objects ever detected, so faint that they appear as mere dots of reddish light scattered across the deepest images of space. Astronomers have come to call them little red dots, and in their simplicity lies one of modern astronomy's greatest mysteries. These objects are challenging everything we thought we understood about how the first galaxies formed in the early universe. The discovery began quietly, as many great discoveries do. When the James Webb Space Telescope first turned its infrared eyes toward the deepest regions of space in late 2022, astronomers expected to see the early universe as a place of gradual development. They thought they would find small primitive galaxies slowly growing over billions of years, eventually becoming the massive structures we see around us today. But scattered throughout those first deep field images were hundreds of tiny red specks that didn't fit any existing models. At first glance, they looked insignificant, like cosmic dust motes floating in the vast darkness. But as astronomers began studying them more carefully, they realized these little red dots were anything but ordinary. The dots appeared to exist in the very early universe, when it was less than a billion years old. That alone made them interesting, but what made them truly puzzling was their impossible combination of properties. They were incredibly compact, appearing roughly 2% the size of our Milky Way galaxy. Yet they were shining with the brightness of objects far, far larger. These mysterious objects are completely undetected before the James Webb Space Telescope, explains Fabio Pacucci, an astrophysicist at Harvard's Center for Astrophysics, who has spent considerable time studying these enigmas. They are arguably the most surprising discovery by JWST to date. As more little red dots were discovered, the mystery deepened. Astronomers found over 300 of them in various Webb observations, all showing similar characteristics. They consistently appeared in the same epoch of cosmic history, mostly around 600 million years after the Big Bang, then seemed to fade away or transform into something else as the universe aged. The challenge was figuring out what these objects actually were. Their red color suggested they might be galaxies shrouded in dust, the kind of dust that forms when massive stars live their brief lives and explode as supernovae. But if they were dust-covered galaxies, they would need to contain an enormous number of stars packed into an impossibly small space. The mathematics didn't work. To shine as brightly as they appeared, these objects would need to contain billions of stars crammed into a volume far too small to accommodate them. The stellar density would be so extreme that it would violate our understanding of how star formation actually works in the real universe. So astronomers began considering other possibilities. Maybe the little red dots weren't galaxies at all, but something else entirely. Maybe they were powered by supermassive black holes, cosmic monsters millions of times more massive than our sun, actively feeding on surrounding material and converting it into brilliant radiation. This idea had merit. Supermassive black holes are incredibly efficient at producing light from infalling matter. A relatively small amount of material spiraling into a black hole can outshine entire galaxies. If the little red dots contained actively feeding black holes, it might explain their incredible brightness despite their compact size. To test this hypothesis, astronomers used Webb spectroscopic instruments to examine the light from little red dots in fine detail. What they found was both illuminating and confusing. About 80% of the little red dots they studied showed spectral signatures consistent with gas rapidly spiraling into black holes, the telltale signs of what astronomers call active galactic nuclei. It does look like there's a good chance that these are actively accreting supermassive black holes. Notes: Gail Kozewski, an astrophysicist at Colby College, who has conducted detailed studies of these objects. The thing that's surprising is they're just really, really common. They're much more common than we would have anticipated. But even the black hole explanation had problems. If little red dots were powered by supermassive black holes, those black holes would need to be impossibly massive for such small host galaxies. Our current understanding of black hole formation suggests that supermassive black holes and their host galaxies should grow together over cosmic time, maintaining a rough proportionality between the black hole's mass and the galaxy's stellar mass. The little red dots seem to violate this relationship completely. They appeared to contain black holes that were far too large for their seemingly modest galactic homes. It was as if someone had installed a massive truck engine in a compact car. Furthermore, little red dots didn't behave like typical active galactic nuclei in other ways. They didn't emit detectable X-rays, which are usually produced when matter falls into black holes. Their spectra didn't show the expected variability that characterizes most actively feeding black holes. They seem to exist in their own category, following their own rules. Recent theoretical work has proposed several possible explanations for these cosmic oddities. One intriguing idea suggests that little red dots formed in extremely rare dark matter halos that spin much more slowly than typical halos. In this scenario, the slow spin of the dark matter structure would naturally create the compact, dense conditions needed to explain the little red dot's unusual properties. Think of this like a carnival ride. When a spinning platform rotates quickly, centrifugal force pushes riders toward the outside edge. But if the platform spins slowly, riders remain closer to the center. Similarly, in a slowly spinning dark matter halo, matter would settle into a much more compact configuration than usual, potentially creating the extreme density observed in little red dots. An even more exotic possibility is that little red dots aren't galaxies or black holes at all, but rather represent something we've never seen before: supermassive stars. These hypothetical objects would be individual stars containing millions of times more matter than our sun, held together by their own gravity for perhaps thousands of years before either exploding or collapsing into black holes. Theoretical models of such supermassive stars predict they would glow with exactly the kind of light observed from little red dots. They would appear red due to their relatively cool surface temperatures, and they would be incredibly bright due to their enormous size. When they finally collapsed, They would form the supermassive black holes that we observe powering quasars in the later universe. This idea is particularly appealing because it might help solve another puzzle in modern astronomy: how supermassive black holes grew so large so quickly in the early universe. If little red dots are supermassive stars in the process of collapsing into black holes, they could represent a crucial missing link in our understanding of cosmic evolution. The discovery of little red dots has also revealed something unexpected about the nature of astronomical discovery itself. These objects were hiding in plain sight in earlier observations, too faint to be detected by previous generations of telescopes, but present nonetheless. It's only Webb's unprecedented infrared sensitivity that finally revealed them. This suggests that the universe may be filled with phenomena that we simply haven't had the tools to observe yet. Each new generation of telescopes reveals not just more of what we expected to find, but entirely new categories of objects that challenge our theories and expand our understanding of what's possible in the cosmos. The study of little red dots is also highlighting the importance of looking beyond our local cosmic neighborhood. Recently, astronomers have discovered similar objects much closer to home, at distances of only 2.5 billion light years, rather than the much more distant early universe locations where they were first found. This suggests that whatever process creates little red dots might not be unique to the early universe. After all, understanding the nearby examples might provide crucial clues about the distant ones, helping astronomers determine whether these objects represent a normal but previously unobserved phase in galaxy evolution or something truly exotic that challenges our fundamental understanding of how cosmic structures form. As Dale Kosevsky puts it, it's been a very, very healthy academic debate as to what's going on with these things. It's exciting because rarely do you find a population of objects where you say, I simply don't know what's going on here. This uncertainty is part of what makes little red dots so scientifically valuable. They represent a genuinely new phenomenon that requires fresh thinking and novel theoretical approaches. They remind us that despite all our advances in understanding the cosmos, the universe is still capable of surprising us with completely unexpected discoveries. The little red dots also demonstrate how much we still have to learn about the early universe. The epoch when these objects appeared was a crucial time in cosmic history, when the first galaxies were forming and the first supermassive black holes were growing. Understanding this period is key to comprehending how the universe evolved from its simple beginnings into the complex, structured cosmos we observe today. Each new observation of little red dots provides another piece of this puzzle. As Webb continues to survey the deep universe and astronomers develop more sophisticated theoretical models, we're gradually building a clearer picture of what these mysterious objects are and what they tell us about the processes that shaped the early cosmos. In the meantime, the little red dots serve as a humbling reminder that the universe is far stranger and more complex than we often imagine. These tiny specks of reddish light, barely visible even to our most powerful telescopes, may hold keys to understanding some of the most fundamental processes in cosmic evolution. They remind us that sometimes the smallest, most innocuous looking objects can harbor the biggest mysteries, and that the universe's most profound secrets are often hidden in the faintest whispers of ancient light, waiting patiently for the right instruments and the right questions to reveal their stories. Over the centuries, Astronomers have had to revise their most fundamental assumptions about the universe. We're going to explore what might be the most profound revision yet, a discovery that could change everything we think we know about the cosmos itself. This story begins with something invisible, something we can't see or touch, but that seems to control the ultimate fate of everything that exists. Scientists call it dark energy, and until very recently, they thought they understood at least one thing about it, that it never changes. Dark energy is the mysterious force that's pushing the universe apart, causing galaxies to accelerate away from each other at an ever increasing pace. It makes up about 70% of everything that exists, yet we have no idea what it actually is. We can only observe its effects, like watching invisible hands slowly stretching the fabric of space itself. For nearly 3 decades, since dark energy was first discovered in 1998, astronomers have assumed it behaves like what Einstein called a cosmological constant. This means it should have exactly the same strength everywhere and at all times, an unchanging property of empty space that will continue pushing the universe apart forever. But new observations from the Dark Energy Spectroscopic Instrument, known as DESI, are suggesting something that has shaken the foundations of modern cosmology. Dark energy might not be constant after all. It might be weakening over time. The DESI project sits atop Kitt Peak in Arizona, where a telescope uses 5,000 robotic arms to simultaneously point optical fibers at different galaxies across the sky. Each fiber captures the light from a distant galaxy, allowing scientists to measure how fast it's moving away from us and how far away it is. Over the past 3 years, DZ has created the largest three-dimensional map of the universe ever made, measuring the distances to nearly 15 million galaxies and bright galactic cores called quasars. Some of these objects are so distant that we're seeing them as they were 11 billion years ago, when the universe was less than a quarter of its current age. What the DZ team found in this vast cosmic map was unexpected. When they combined their measurements with observations from other telescopes, including studies of exploding stars and the ancient light left over from the Big Bang, a consistent pattern emerged. The data suggested that dark energy was stronger in the past and has been gradually weakening over billions of years. The results we're seeing are truly fascinating, explains Heejong Seo, a physicist at Ohio University who helped lead the analysis. When we first detected a strong indication of evolving dark energy last year, we were excited, but there was also a healthy skepticism wondering if it might just be a statistical anomaly. The team spent months double-checking their work, adding more data and testing their methods. But instead of the signal disappearing, it grew stronger. The evidence now approaches what scientists call 4 sigma confidence, meaning there's less than a 1 in 15,000 chance that this pattern is just a statistical coincidence. If these findings hold up, they would represent what some researchers are calling the most significant discovery in cosmology since dark energy itself was found. The implications extend far beyond academic interest. They could fundamentally change our understanding of what the universe is made of and where it's headed. To understand why this matters, we need to think about what dark energy actually does. Imagine the universe as a balloon being inflated. The ordinary matter and dark matter act like weights attached to the balloon's surface, trying to slow down the inflation through their gravitational pull. Dark energy acts like the pump, pushing outward and causing the balloon to expand faster and faster. If dark energy were truly constant, this cosmic inflation would continue accelerating forever. Galaxies would move farther and farther apart until billions of years from now, our night sky would become almost completely empty. Stars would eventually burn out, black holes would evaporate, and the universe would end in what cosmologists call the heat death, a cold, dark, empty expanse. But if dark energy is weakening, as the DESA data suggests, the future becomes much less certain. A weakening dark energy might eventually lose its battle against gravity. The expansion of the universe could slow down, stop, and perhaps even reverse, leading to a big crunch where everything collapses back together. Alternatively, dark energy might strengthen again, or its behavior might be more complex than simple weakening. Some theoretical models suggest it could vary in cycles, or that different regions of space might experience different amounts of dark energy. The key to today's discovery lies in something called baryon acoustic oscillations, or BAOs. These are subtle patterns in how galaxies are distributed across space, remnants of sound waves that traveled through the early universe before stars and galaxies formed. Think of these patterns like ripples frozen in time. In the hot, dense early universe, pressure waves created by the interplay of matter and radiation propagated outward like sound waves in air. When the universe cooled enough for atoms to form, about 380,000 years after the Big Bang, these waves became frozen into the structure of matter itself. Today, we can still see the effects of these ancient sound waves in the way galaxies are arranged. They show up as a slight preference for galaxies to be separated by a specific distance, about 450 million light years. This distance acts like a cosmic ruler, allowing astronomers to measure how much the universe has expanded at different periods in its history. By tracking how this cosmic ruler has changed size over 11 billion years, the DZ team can reconstruct the history of cosmic expansion. They can see how dark energy's influence has varied over time, from the distant past to the present day. What they found was subtle but consistent. The data suggests that dark energy's influence peaked sometime in the past and has been gradually declining since. The effect is small, perhaps a 10% decrease over the last 4.5 billion years, but it's persistent across multiple independent measurements. It's not just that the data continue to show a preference for evolving dark energy, notes Seshadri Nadathur, a cosmologist at the University of Portsmouth who worked on the analysis. The evidence is stronger now than it was. We've also performed many additional tests compared to the first year, and they're making us confident that the results aren't driven by some unknown effect in the data that we haven't accounted for. The discovery is forcing physicists to reconsider their most basic assumptions about the nature of reality. For decades, dark energy has been one of the deepest mysteries in science. We know it exists because we can see its effects, but we have no idea what it actually is or why it has the exact strength we observe. One possibility is that dark energy isn't a property of empty space at all, but rather a field that permeates the universe, similar to the fields that give particles their mass or create magnetic forces. Such fields can naturally change over time, growing stronger or weaker as conditions in the universe evolve. Another possibility is that our understanding of gravity itself needs to be revised. Perhaps Einstein's equations, which have served us well for over a century, are incomplete when applied to the largest scales of space and time. Modified theories of gravity might naturally produce the apparent weakening of dark energy without requiring any new mysterious force. The implications extend beyond physics into philosophy. If dark energy is not constant, it suggests that the universe is more dynamic and unpredictable than we thought. We may not be living in a stable, well understood cosmos, but rather in a system that's still evolving in fundamental ways. For people like me, working on this for 25 years, we didn't expect this to happen in our lifetime, says Mustafa Ishaq Bushaki, a cosmologist at the University of Texas at Dallas, who helped coordinate the DESA analysis. If the evidence continues to grow, it will be monumental for cosmology and all of physics. The research also highlights how much we still don't understand about the universe we inhabit. Despite centuries of scientific progress, we find ourselves confronted with the possibility that 70% of reality consists of something we can't explain, and that this something might be changing in ways we're only beginning to detect. The DESI team is careful to emphasize that their findings are not yet definitive. Science requires extraordinary evidence for extraordinary claims, and the claim that dark energy varies over time is certainly extraordinary. More data will be needed to reach the 5 sigma level of confidence that physicists typically require to announce a discovery. But other telescopes are already providing supporting evidence. The Dark Energy Survey, using a different technique involving exploding stars called supernovae, has found similar hints that dark energy might be evolving. When combined with DESA's measurements, the evidence becomes more compelling. Over the next few years, several new telescopes will come online with even more powerful capabilities for studying dark energy. The Vera Rubin Observatory in Chile will survey billions of galaxies. NASA's Roman Space Telescope will study dark energy from space, and the European Euclid mission will map cosmic structure with unprecedented precision. These new instruments will either confirm DEZ's findings or reveal them to be an artifact of incomplete data. Either outcome will be scientifically valuable, but confirmation would mark a turning point in our understanding of the universe. The potential discovery of evolving dark energy reminds us how much mystery still surrounds us. We live in a universe where the dominant component of reality is not just invisible and unexplained, but possibly changing in ways that could determine the ultimate fate of everything that exists. As we continue to probe these cosmic mysteries, we're reminded that the universe is not a static, predictable machine, but a dynamic, evolving system full of surprises. Each new discovery opens doors to questions we hadn't even thought to ask, revealing layers of complexity and wonder that extend far beyond our current understanding. Whether dark energy is truly weakening or our measurements are revealing some other unexpected phenomenon, we're clearly standing at the threshold of new knowledge about the deepest workings of the cosmos. The universe, it seems, still has plenty of secrets left to share. Continuing our exploration through the cosmos, we now encounter what might be the single most perplexing star in our galaxy. This isn't a distant galaxy or an exotic black hole. It's a relatively ordinary star, not so different from our own sun, located about 1,400 light years away in the constellation Cygnus. Yet this star has exhibited behavior so bizarre, so completely unprecedented, that it has baffled astronomers for nearly a decade. Its official designation is KIC 84628252, but the astronomical community has given it a more personal name, Tabby's star, after Tabitha Boyajian, the astronomer who first brought its strange behavior to the world's attention. The story begins, as many modern astronomical discoveries do, with citizen scientists. In the early 2010s, thousands of volunteers around the world were participating in a project called Planet Hunters, examining data from NASA's Kepler Space Telescope. Their task was simple in concept, but enormous in scope. Look through light curves from over 150,000 stars, searching for the telltale dips in brightness that indicate an orbiting planet. Most of what they found was routine, stars that varied predictably, stars with planets crossing in front of them at regular intervals, stars that pulsed with mathematical precision. But among all this cosmic regularity, citizen scientists began flagging one star that seemed to break every rule. This star would dim suddenly and dramatically, sometimes by just 1%, sometimes by an astonishing 22%. The dips were completely unpredictable, lasting anywhere from days to weeks before the star returned to its normal brightness. There was no pattern, no regularity, no explanation that fit any known astronomical phenomenon. When professional astronomers first examined these reports, many suspected the unusual behavior was simply an error in the data or an artifact of the telescope's instruments. But as they looked more carefully, they realized the citizen scientists had found something genuinely extraordinary. I was fascinated by how crazy it looked. Tabitha Boyajian recalls, aliens should always be the last hypothesis you consider, but this looked like something you would expect an alien civilization to build. The brightness variations were unlike anything astronomers had ever seen from a normal star. When a planet passes in front of its star, it typically blocks less than 1% of the light, and it does so regularly, following the predictable rhythm of its orbit. But Tabby's star was dimming by enormous amounts at completely random intervals. The magnitude of these dips ruled out planets as an explanation. Even a planet as large as Jupiter, if it somehow orbited close enough to this star, would block only about 1% of its light. To create the 22% dimming that Tabby's star sometimes exhibited, you would need something roughly the size of the star itself passing in front of it. This led astronomers to consider increasingly exotic explanations. Perhaps the star was surrounded by a massive swarm of comets, their dust tails periodically obscuring its light. Maybe a planet had recently been shattered, creating a debris field that was slowly dispersing. Or perhaps we were witnessing some other catastrophic event playing out on cosmic timescales. But then Penn State astronomer Jason Wright suggested a possibility that captured the public imagination. Maybe we were seeing evidence of an alien megastructure. Perhaps an advanced civilization had built something enormous around this star, a vast construction project designed to harvest stellar energy. The structure could be partially blocking the star's light as it moved through its orbit, creating the irregular dimming we observed. The idea wasn't entirely far-fetched. Theoretical physicists had long speculated about Dyson spheres, hypothetical megastructures that an advanced civilization might build around a star to capture its energy output. If such structures existed, they might appear exactly as Tabby's star was behaving, with irregular segments of the sphere passing between us and the star at unpredictable intervals. Wright was careful to emphasize that this was an extremely unlikely explanation, but the mere possibility of alien technology sent ripples of excitement through both the scientific community and the general public. Here, finally, was a cosmic mystery that could potentially have the most profound implications imaginable for humanity's place in the universe. The speculation intensified when another astronomer, Bradley Schaefer of Louisiana State University, examined historical records and found that Tabby's star had been gradually dimming for over a century. Analysis of photographic plates from Harvard College Observatory showed that the star had become about 14% fainter between 1890 and 1989. Combined with the dramatic short-term dips, this suggested that something ongoing and long-term was affecting the star. But even as the alien megastructure theory gained media attention, astronomers were working methodically to test more mundane explanations. They began organizing coordinated observations, waiting patiently for the next dimming event so they could study it with multiple telescopes simultaneously. In May 2017, their patience was rewarded. Tabby's star began dimming again, and observatories around the world turned their attention to this enigmatic object. For the first time, astronomers were able to observe a dimming event in real time, measuring how the star's light changed across different wavelengths and looking for clues about what might be causing the obstruction. The results were both illuminating and disappointing for those hoping for evidence of alien technology. The dimming varied with the color of light, being more pronounced in blue and ultraviolet wavelengths than in red and infrared. This wavelength-dependent dimming was exactly what you would expect if the star's light were being scattered by small particles of dust, not blocked by a solid megastructure. Subsequent observations confirmed this pattern. Whatever was causing Tabby's star to dim appeared to be composed of tiny particles, perhaps no larger than grains of smoke. A solid alien construction would block all wavelengths of light equally, but dust preferentially scatters shorter, bluer wavelengths while allowing longer, redder light to pass through more easily. Dust is most likely the reason why the star's light appears to dim and brighten. Voyager announced after analyzing the new data. The different colors of light being blocked at different intensities tells us that whatever is passing between us and the star is not opaque, as would be expected from a planet or alien megastructure. But solving one mystery only created others. If dust was causing the dimming, where was it coming from? Why was it distributed so irregularly around the star? And what could explain both the dramatic short-term dips and the long-term gradual fading? One possibility involves comets, but not in the way originally conceived. Instead of a family of intact comets orbiting the star, the dimming might be caused by dust from comets that have already broken apart. Perhaps a massive comet wandered too close to Tabby's star sometime in the past and was shattered by tidal forces. The resulting debris field could create the irregular dust clouds we observe today. Another intriguing theory suggests that we might be witnessing the destruction of an exomoon, a moon that was originally orbiting a planet but got captured by the star's gravity. As this captured moon spirals closer to the star, it would gradually evaporate, creating clouds of dust and gas that could explain both the short-term dimming events and the long-term decline in brightness. Recent research has even proposed that Tabby's star might not be as unusual as once thought. In 2019, astronomers identified 21 other stars showing similar irregular dimming behavior, suggesting that whatever causes this phenomenon might be more common than previously believed. Yet, despite years of intensive study, Tabby's star continues to guard its secrets. The dust explanation accounts for many of the observations, but doesn't fully explain the timing, magnitude, and irregular nature of the dimming events. Each new observation adds pieces to the puzzle, but the complete picture remains frustratingly elusive. The James Webb Space Telescope has recently turned its infrared eyes toward Tabby's star, hoping to detect thermal emission from whatever dust clouds are causing the dimming. These observations might finally provide the definitive evidence needed to understand this cosmic enigma. The story of Tabby's star illustrates both the power and limitations of modern astronomy. We have telescopes capable of detecting minute changes in a star's brightness across thousands of light years of space, yet we struggle to explain what we see. It reminds us that the universe is still full of phenomena that challenge our understanding and push the boundaries of our theories. Perhaps more importantly, Tabby's star demonstrates the valuable role that citizen scientists can play in astronomical discovery. Without the dedicated volunteers who first noticed its unusual behavior in the Kepler data, this mystery might have gone undetected for years. Their careful attention to detail revealed one of the most intriguing puzzles in modern astronomy. The search for an explanation continues, driven by the same curiosity that has always motivated scientists. Whether the ultimate answer involves exotic stellar phenomena, catastrophic collisions, or processes we haven't yet imagined, Tabby's star has already taught us that the cosmos is far stranger and more dynamic than we often assume. The star also serves as a reminder that the universe doesn't always conform to our expectations or our models. Sometimes nature creates phenomena so unusual that they force us to expand our thinking and consider possibilities we never imagined. In doing so, these cosmic mysteries push the boundaries of human knowledge and understanding. As observations continue and new data accumulates, we edge closer to solving the riddle of Tabby's star. But regardless of what explanation ultimately proves correct, this enigmatic star has already secured its place in the annals of astronomy as one of the most fascinating and perplexing objects in our galaxy. The dimming mystery reminds us that the universe still holds secrets, that there are phenomena occurring in the depths of space that we don't yet understand. Each mysterious star, each unexplained signal, each anomalous observation represents an opportunity to learn something new about how the cosmos works. In the end, Tabby's star stands as a testament to the ongoing adventure of astronomical discovery. It shows us that even in an age of sophisticated telescopes and advanced theories, the universe can still surprise us with behavior so strange that it challenges everything we thought we knew about stellar physics. Whatever is causing this star to dim in such an unprecedented way, the eventual explanation will undoubtedly teach us something fundamental about the processes that govern stellar systems. And in the meantime, Tabby's star continues to flicker mysteriously in the constellation Cygnus, patiently keeping its secrets while astronomers around the world work to unravel one of the greatest puzzles in modern astronomy. As we venture deeper into the catalog of cosmic mysteries, we encounter perhaps the most enigmatic discovery of all. It's an object so unprecedented that astronomers have struggled even to describe what they're looking at. They've given it a simple name that captures both its appearance and its mystery. Punctum, from the Latin word for point or dot. This isn't a story about something vast and distant, like a colliding galaxy billions of light years away. Instead, it's about something remarkably small and relatively nearby that has managed to completely confound our understanding of what's possible in the universe. The discovery began in the most mundane way imaginable. Elena Shablovinskaya, an astronomer at the Instituto de Estudios Astrofísicos at the Universidad Diego Portales in Chile, was conducting routine observations with the Atacama Large Millimeter Array, or ALMA, one of the most sensitive radio telescope complexes on Earth. Her target was NGC 4945, a well-known starburst galaxy located about 11 million light-years away in the constellation Centaurus. This galaxy had been studied many times before. It's what astronomers call an active galaxy, with a supermassive black hole at its center and regions of intense star formation throughout its spiral arms. Shablovinskaya wasn't expecting to find anything particularly unusual, but as she analyzed the data from ALMA's array of radio dishes, she noticed something that made her pause. There, about 200 light years away from the galaxy's central black hole, was a tiny point of light that seemed almost impossibly bright in the millimeter wavelengths her telescope was designed to detect. At first, she thought it might be an error in the data, or perhaps some kind of instrumental artifact, but as she looked more carefully, switching Alma's array into polarized light mode, something extraordinary happened. Everything else in the galaxy seemed to fade away. Even the bright central black hole, which had been dominating the observations, virtually disappeared from view. Only this one tiny dot remained, shining with an intensity that defied explanation. Everything else disappeared. Shablovinskaya later recalled even the bright central black hole, and only this little dot remained. When she began calculating the actual brightness of this object, the numbers seemed almost impossible to believe. Punctum was emitting as much energy in just a handful of millimeter wavelengths as a star like Sirius emits across the entire electromagnetic spectrum. But unlike Sirius, which we can see easily with the naked eye, punctum was completely invisible in normal light, X-rays, and most radio wavelengths. When you put it into context, Shablovinskaya explained, punctum is astonishingly bright, 10,000 to 100,000 times more luminous than typical magnetars, around 100 times brighter than microquasars, and 10 to 100 times brighter than nearly every known supernova, with only the Crab Nebula surpassing it among star-related sources in our galaxy. This comparison is worth pausing to consider. Magnetars are neutron stars with magnetic fields, trillions of times stronger than Earth's, among the most powerful objects in the known universe. Microquasars are stellar mass black holes that launch jets of matter at nearly the speed of light. Supernovae are exploding stars that can briefly outshine entire galaxies. Yet this tiny dot in NGC 4945 was outshining almost all of them. Even more remarkable was the fact that punctum appeared to be incredibly small. Despite ALMA's exceptional resolution, the EBITS remained essentially a point source, suggesting it was no more than about 6.5 light-years across. For comparison, the Crab Nebula, the only object that rivals punctum's brightness in similar wavelengths, spans about 11 light-years and is the expanding remnant of a supernova explosion that occurred nearly 1,000 years ago. What could possibly create such enormous energy output in such a compact space? And why was it visible only in this narrow slice of the electromagnetic spectrum? The clues lay in the polarization of punctum's light. When ALMA analyzed how the radio waves were oriented as they arrived at Earth it found something extraordinary. About 50% of the light was polarized, meaning the electromagnetic waves were all aligned in the same direction rather than scattered randomly. In astronomy, highly polarized light is usually a signature of synchrotron radiation, the same process that creates the aurora on Earth, but scaled up to cosmic proportions. This occurs when electrically charged particles are accelerated to tremendous speeds by powerful magnetic fields, causing them to spiral along magnetic field lines and emit radiation in the process. For light to be so highly polarized, the magnetic field creating it would need to be extraordinarily well organized and incredibly strong. It would be like finding a perfectly straight road in the middle of a chaotic city, suggesting some kind of organizing principle that astronomers had never encountered before. Shablovinskaya and her colleagues spent months trying to match punctum's properties to known types of cosmic objects. They considered pulsars, rapidly spinning neutron stars that emit lighthouse like beams of radiation. But pulsars are typically much fainter in millimeter wavelengths than what punctum displayed. They considered supernova remnants, the expanding shells of gas and debris left behind when massive stars explode. Some of these can indeed be very bright in millimeter waves and can produce polarized radiation, but supernova remnants are typically much larger than punctum appears to be, and their magnetic fields are usually too chaotic to produce such highly organized polarization. They looked at microquasars, stellar mass black holes that launch jets of particles into space. These can certainly produce polarized synchrotron radiation, but even the brightest known microquasars fall far short of punctum's luminosity. They even considered more exotic possibilities, like magnetars, neutron stars with the strongest magnetic fields known in the universe. While magnetars can produce highly polarized radiation, they're typically invisible to ALMA and other millimeter wave telescopes. Every comparison fell short. Punctum didn't fit comfortably into any existing category of astronomical object. At the moment, punctum really stands alone. Shablovinskaya concluded. It doesn't fit into any of the known categories, and to be honest, nothing like this has been observed in any of the previous millimeter wave surveys, mainly because, until recently, we didn't have anything as sensitive and as accurate as ALMA. The implications of this discovery extend far beyond just adding another entry to the catalog of unusual cosmic objects. Punctum suggests that there are phenomena occurring in the universe that our current theories and models simply don't account for. It's a reminder that despite all our advances in astronomy and astrophysics, the cosmos is still capable of surprising us with completely unprecedented behavior. One possibility is that punctum represents an extreme version of a known phenomenon. Perhaps it's a magnetar that happens to exist in a very unusual environment, one that amplifies its emission in ways we've never seen before. Maybe it's a supernova remnant that's interacting with exceptionally dense surrounding material, creating conditions that boost its brightness far beyond normal levels. Another possibility is more radical, that punctum is genuinely something new, a type of object that we've never discovered before because we've never had sensitive enough instruments to detect it. The universe might be populated with similar objects that have remained invisible until now, waiting for the right combination of telescope sensitivity and observational technique to reveal them. The steady nature of punctum's emission adds another layer to the mystery. Unlike many cosmic phenomena, which vary over time or appear as brief flashes. Punctum has maintained essentially constant brightness across all observations from 2019 to 2023. This rules out many types of explosive or transient events and suggests that whatever is powering punctum is a stable, long-term process. The James Webb Space Telescope has recently begun observing punctum in infrared wavelengths, hoping to detect thermal emission that might provide additional clues about its nature. These observations might finally reveal whether the object is surrounded by gas or dust that could explain some of its unusual properties. Meanwhile, other telescopes around the world are searching for similar objects in other galaxies. If punctum is truly a new type of cosmic phenomenon, there should be others like it waiting to be discovered. Finding additional examples would help astronomers understand whether punctum is a cosmic fluke or represents a new class of objects that we've been missing. The discovery also highlights the importance of advanced astronomical instruments like ALMA. These facilities don't just help us see farther and more clearly, they sometimes reveal entirely new categories of phenomena that were previously invisible to us. Each new generation of telescopes opens up fresh windows on the universe, potentially revealing aspects of cosmic behavior that we never suspected existed. Punctum reminds us that the universe is still full of surprises, still capable of producing phenomena that challenge our most fundamental assumptions about how cosmic objects behave. It's a tiny point of light in a distant galaxy that has managed to upend years of astronomical theory and classification. As research continues and more data accumulates, astronomers hope to finally understand what makes punctum so unique. But regardless of what explanation ultimately emerges, this mysterious object has already taught us something important, that the cosmos is far stranger and more varied than we often assume. The existence of punctum suggests that our current understanding of extreme astrophysical processes is incomplete. There are clearly phenomena occurring in the universe that operate according to principles we haven't yet discovered or fully understood. Each mysterious object we find expands the boundaries of what we consider possible in the cosmic arena. In the end, punctum stands as both a humbling reminder of our ignorance and an exciting promise of discoveries yet to come. It represents the kind of genuine mystery that drives scientific inquiry forward, the type of observation that forces us to reconsider our models and expand our understanding of how the universe actually works. This tiny, brilliant dot in NGC 4945 may eventually be explained by extensions of existing theory, or it may require entirely new physics to understand. Either way, it has already secured its place in the history of astronomy as one of the most puzzling and significant discoveries of the modern era, a punctuation mark in our understanding of the cosmos that demands a fundamental reassessment of what we thought we knew about the universe. In parallel to these grand cosmic mysteries, we turn our attention to worlds that exist at the extremes of visibility. Some planets shine like polished mirrors, reflecting nearly all the light that touches them. Others absorb light so completely that they seem to exist as holes cut from the fabric of space itself. Let's begin with the shiniest world ever discovered, a planet that has earned the nickname the universe's largest mirror. About 260 light years from Earth, in the constellation Sculptor, orbits a world called LTT 9779. This planet reflects an astonishing 80% of the light that falls on it from its star. To put this in perspective, Our own Earth reflects only about 30% of the sunlight that reaches it. Venus, the brightest object in our night sky after the moon, reflects about 75% of the sun's light thanks to its thick clouds of sulfuric acid. But LTT 9779b outshines even Venus, making it the most reflective planet ever found anywhere in the universe. What makes this discovery particularly remarkable is that LTT 9779b shouldn't be able to maintain such reflectivity. The planet orbits its star every 19 hours, closer than Mercury orbits our Sun. The star facing side of the planet is heated to about 2000 degrees Celsius, hot enough to melt copper and turn rock into vapor. At such extreme temperatures, any normal clouds should simply evaporate away, yet somehow LTT 9779b maintains a brilliant mirror-like surface that deflects most of the intense radiation back into space. The secret lies in the planet's extraordinary atmospheric composition. Instead of water clouds like those on Earth, or even the sulfuric acid clouds of Venus, this world is shrouded in metallic clouds made of titanium and silicates, the basic components of glass and sand. Imagine a burning world close to its star, with heavy clouds of metals floating aloft, raining down titanium droplets, explains James Jenkins, an astronomer at Diego Portales University who helped study this remarkable world. The formation of these metallic clouds follows a process similar to what happens in a steamy bathroom after a hot shower. Just as hot water vapor can saturate the air until it condenses on cooler surfaces, the atmosphere of LTT 9779b becomes so saturated with vaporized metals and silicates that they condense into reflective droplets. Even at these extreme temperatures, the planet's ability to maintain such reflective clouds is crucial to its survival. These metallic mirrors prevent the planet from absorbing too much heat and evaporating completely. At the same time, the heavy metallic composition makes the planet and its atmosphere more massive and harder for stellar radiation to strip away. This allows LTT 9779b to exist in what astronomers call the Neptune Desert, a region close to stars where planets of this size typically cannot survive. Most worlds like this would have their atmospheres completely blown away by stellar winds, leaving behind only a rocky core. But the reflective clouds act as a cosmic sunscreen, allowing this world to thrive where others would perish. The discovery came from the European Space Agency's TEOPS telescope, which detected the subtle changes in brightness as the planet orbited its star. When the planet's day side faced Earth, the reflected light made the entire system slightly brighter. When the planet moved behind its star, this extra brightness disappeared. The precision required to measure these tiny variations is extraordinary, like detecting the difference in brightness caused by a coin held up against a lighthouse beam from several miles away. But if some worlds shine like mirrors, others represent the opposite extreme. About 750 light years away, in the constellation Draco, lurks a world so dark it defies easy explanation. This planet, known as Tres 2b, reflects less than 1% of the light that strikes it, making it darker than coal, darker than black acrylic paint, darker than any known substance on Earth. Tres 2b is a Jupiter-sized gas giant that orbits its sun-like star every 2.5 days. Like many hot Jupiter planets, it's tidally locked, with one side permanently facing its star and the other side locked in eternal night. But unlike other hot Jupiters, which typically reflect at least some starlight, Tres 2b seems to swallow light almost completely. The planet's extreme darkness came as a surprise to astronomers. Jupiter, for comparison, is swathed in bright clouds of ammonia that reflect more than a third of the sunlight reaching it. Even taking into account Tres 2b's much higher temperature, which prevents the formation of reflective ammonia clouds, astronomers expected it to reflect at least a few percent of incoming light. Instead, they discovered a world that absorbs light more completely than any known material. The planet is so dark that if you could somehow visit it, you would find it almost impossible to see, even though it orbits much closer to its star than Mercury does to our Sun. It's just ridiculous how dark this planet is, how alien it is compared to anything we have in our solar system, says David Kipping, the Harvard astronomer who led the discovery. It's darker than the blackest lump of coal, than dark acrylic paint you might paint with. Despite its incredible darkness, Test 2b is not completely invisible. The planet is so hot from its proximity to its star that it glows with its own thermal radiation, like a piece of charcoal in a fire. This faint reddish glow is the only light the planet emits, making it appear like a glowing ember floating in space. What causes such extreme darkness? The planet's atmosphere likely contains light-absorbing chemicals such as vaporized sodium and potassium, or gaseous titanium oxide. These substances can absorb visible light very efficiently, preventing it from being reflected back into space. But even these known light-absorbing compounds cannot fully explain Tres 2b's extreme darkness. The mystery deepens when we consider that Tres 2b is not unique. Astronomers have discovered other remarkably dark planets, suggesting that such extreme light absorption might be more common than previously thought. Each new discovery adds to the puzzle of understanding what creates these cosmic shadows. Between these extremes of brightness and darkness lie other worlds with equally remarkable optical properties. Take Butter Wasp 178, Beshal the planet, where the very rocks rain from the sky. This ultra-hot Jupiter orbits so close to its star that the day side reaches temperatures of over 2,500 degrees Celsius, hot enough to vaporize silicon-based rocks. On this world, the intense heat causes silicate minerals to evaporate into the atmosphere, where they mix with the planet's hydrogen and helium. Supersonic winds, moving at speeds of over 3,000 kilometers per hour, carry these vaporized rocks from the blazing day side to the cooler night side. As the rock vapor cools on the night side, it condenses back into solid particles that fall as rain. But this isn't rain as we know it. Instead of water droplets, liquid gems and molten rock pour from the alien sky, creating a landscape that exists nowhere else in our experience. It's like having a blast furnace in the sky, explains one researcher studying this extraordinary world. The planet represents a natural laboratory for studying matter under conditions so extreme that they cannot be replicated on Earth. Then there are worlds like WASP 17b, where clouds are made entirely of quartz crystals. This puffy hot Jupiter has an atmosphere so hot that even quartz, normally a solid crystal we find in rocks and sand, exists as tiny floating nanocrystals in the upper atmosphere. These quartz clouds are just 10 nanometers across, about 1/10,000th the width of a human hair. They form in the planet's atmosphere, much like water clouds form on Earth, but at temperatures exceeding 1500 degrees Celsius. The discovery of quartz clouds was completely unexpected and has forced astronomers to reconsider what kinds of materials can form atmospheric particles in extreme environments. The variety of these extreme worlds tells us something profound about planetary formation and evolution. Each represents a natural experiment in physics and chemistry, showing us what happens when matter is subjected to conditions far beyond anything we experience on Earth. The shiniest planets reveal the importance of atmospheric composition in planetary survival. Their reflective clouds act as cosmic shields, protecting them from their star's intense radiation and allowing them to exist in environments where other planets would be quickly destroyed. The darkest planets show us that matter can absorb light more completely than we might have imagined possible. They challenge our understanding of atmospheric chemistry and force us to consider exotic processes that can trap and destroy photons so efficiently. Between these extremes, we find worlds with atmospheric compositions that would have been pure science fiction just a few decades ago. Planets where precious metals rain from metallic clouds, where quartz crystals float in superheated atmospheres, where the very stuff of geology becomes weather. These discoveries also highlight the incredible diversity of planetary systems throughout the galaxy. Our solar system, with its mix of rocky inner planets and gas giants in the outer reaches, represents just one possible arrangement. The universe has created worlds that span the entire spectrum from mirror bright to shadow dark, each one a unique expression of the physical processes that govern planetary formation and evolution. As our telescopes become more sophisticated and our detection methods more sensitive, we continue to discover new categories of extreme worlds. Each one expands our understanding of what's possible in planetary science and challenges us to think more creatively about the processes that shape worlds throughout the cosmos. These extreme planets serve as natural laboratories where we can study matter and energy under conditions impossible to recreate on Earth. They provide insights into atmospheric physics, chemistry, and dynamics that help us understand not just distant worlds, but our own planet. The shiniest and darkest worlds remind us that the universe is capable of creating conditions and phenomena that stretch our imagination. They show us that the cosmos is not bound by the familiar examples we see in our own solar system, but instead represents a vast laboratory where nature experiments with every possible combination of matter, energy, and environment. As we continue to discover and study these remarkable worlds, we gain a deeper appreciation for the incredible diversity and creativity of the universe. Each extreme planet teaches us something new about the fundamental processes that govern matter and energy, expanding our understanding of physics, chemistry, and the beautiful complexity of the cosmos we inhabit. In the end, these contrasting worlds, from the universe's largest mirror to its darkest shadows, stand as testaments to the extraordinary range of conditions that exist throughout the galaxy, reminding us that reality often exceeds even our most imaginative speculations about what might be possible in the vast reaches of space. Moving away from distant cosmic oddities, we now turn our attention to something much closer to home, yet equally mysterious. These are the Fermi bubbles, two enormous lobes of superheated plasma that balloon above and below the center of our own Milky Way galaxy. They stretch across 50,000 light years from tip to tip, making them roughly half as wide as our entire galaxy. To put this in perspective, If the Milky Way were the size of a dinner plate, these bubbles would be like two balloons attached to opposite sides, each one nearly the size of the plate itself. The story of their discovery is a reminder of how much we still don't know about our own cosmic neighborhood. For decades, astronomers had been studying the center of our galaxy with every instrument at their disposal. They mapped its stars, traced the orbit of gas clouds around the central black hole, and measured radiation across the electromagnetic spectrum. Yet somehow, these enormous structures remained completely invisible to us. The breakthrough came in 2010 when Doug Finkbeiner, an astronomer at the Harvard Smithsonian Center for Astrophysics, was analyzing data from NASA's Fermi Gamma Ray Space Telescope. He was looking for something entirely different, working with graduate students Meng Su and Tracy Sladier to map the faint glow of gamma rays that permeates our galaxy. Gamma rays are the highest energy form of light in the universe, produced when cosmic rays, particles moving at nearly the speed of light, collide with gas and dust in space. The sky is filled with a diffuse fog of these gamma rays, creating a background glow that astronomers must carefully account for when studying specific objects. But as Finkbeiner and his team worked to map this gamma ray fog, they noticed something unprecedented. Hidden within the noise of the background radiation were two enormous structures that nobody had ever seen before. What we see are two gamma ray emitting bubbles that extend 25,000 light years north and south of the galactic center. Finkbeiner explained when the discovery was announced. We don't fully understand their nature or origin. The bubbles were unlike anything astronomers had encountered. They had remarkably sharp edges, suggesting they were created by some kind of explosive event rather than a gradual process. They were perfectly symmetrical, extending equal distances above and below the galactic plane, and they were bright, much brighter in gamma rays than the surrounding regions of the galaxy. The discovery was so unexpected that it took months for the scientific community to accept it. How could structures this large exist at the heart of our galaxy without anyone noticing them before? The answer lay in the subtle nature of gamma ray astronomy and the sophisticated data processing required to tease signals from the cosmic background noise. Previous gamma ray telescopes had neither the sensitivity nor the resolution to detect the bubbles. The Fermi telescope, with its large area telescope instrument, was the first to provide both the broad sky coverage and the precision needed to map these faint structures against the bright background of galactic gamma ray emission. But discovering the bubbles was only the beginning of the mystery. The more astronomers studied them, the stranger they became. These structures were filled with cosmic rays, high-energy particles moving at tremendous speeds. Yet cosmic rays typically spread out randomly as they propagate through space. How were they confined into such well-defined, symmetrical shapes? The sharp boundaries of the bubbles suggested they were somehow contained, perhaps by magnetic fields or by shock waves propagating through the galactic medium. But what kind of event could create structures this large and perfectly organized? Two main theories emerged to explain the Fermi bubbles, each pointing to dramatically different processes in our galaxy's recent past. The first involved our galaxy's central supermassive black hole, an object called Sagittarius A star that contains more than 4 million times the mass of our Sun. Today, this black hole is relatively quiet, consuming material at a leisurely pace and producing only modest amounts of radiation. But black holes are capable of much more dramatic behavior, when they have abundant fuel. When large amounts of matter fall toward a black hole, the material heats up and forms an accretion disk that can outshine entire galaxies. Some of this infalling matter doesn't actually cross the black hole's event horizon. Instead, it gets caught up in the black hole's magnetic field and is accelerated to enormous speeds, creating jets of particles that stream away from the black hole at a significant fraction of the speed of light. Many distant galaxies show evidence of such activity, with jets extending millions of light years from their central black holes. The theory suggests that our own galaxy's black hole might have gone through such an active phase several million years ago, creating the jets that we now see as the Fermi bubbles. The timeline fits remarkably well. Computer simulations suggest that jets from our central black hole would take several million years to reach their current extent. The bubbles appear to be roughly this age based on various astronomical evidence, including the recent discovery that they may be much younger than originally thought. Evidence for this black hole activity theory comes from observations of the Large Magellanic Cloud, a small galaxy that orbits the Milky Way. This satellite galaxy has a long tail of gas that appears to have been ionized by some energetic event in our galaxy's past. The timing and characteristics of this ionization match what astronomers would expect if our central black hole had indeed been active several million years ago. But there's an alternative explanation that doesn't require exotic black hole jets. The center of our galaxy is also home to intense star formation activity, with massive star clusters packed into a relatively small region. These massive stars live fast and die young, exploding as supernovae after just a few million years. A burst of star formation in the galactic center could have produced numerous massive stars that subsequently exploded in quick succession. The combined energy from these supernovae could have driven a galactic superwind, pushing hot gas and cosmic rays outward to create the structures we observe today. The stellar explanation has its own appeal because we can directly observe evidence for recent star formation in the galactic center. There are indeed massive young star clusters there, and we know that such stellar populations can drive powerful galactic winds in other galaxies. Recent discoveries have added new dimensions to the mystery. In 2020, the Eurocida X-ray telescope discovered companion structures to the Fermi bubbles, enormous lobes of X-ray emission that extend even farther from the galactic center. These Eurocida bubbles appear to represent shocked gas in the intergalactic medium surrounding our galaxy, suggesting that whatever created the Fermi bubbles was powerful enough to affect the space between galaxies. Even more intriguing was the discovery in 2025 of cold hydrogen clouds deep within the Fermi bubbles. These clouds, detected by the Green Bank telescope, shouldn't exist in such an extreme environment. The bubbles are filled with gas, heated to millions of degrees, moving at speeds of nearly 1,000,000 miles per hour. Any cold material should be quickly heated and dispersed by these conditions. Think of it like dropping an ice cube into boiling water, explains Rongman Bordeloy, who led the discovery. A small one melts quickly, but a larger one lasts longer, even as it dissolves. The survival of these cold clouds provides important clues about the age of the Fermi bubbles. Computer simulations suggest that such clouds could only survive for a few million years in the hostile environment of the bubbles. Their presence indicates that the bubbles are much younger than originally thought, perhaps only a few million years old rather than tens of millions. This relatively young age has profound implications for understanding what created the bubbles. It means that whatever explosive event formed these structures occurred recently enough that early human ancestors might have witnessed its effects, had they possessed the ability to detect gamma rays. The youth of the bubbles also suggests that such events might be relatively common in our galaxy's history. If the Fermi bubbles formed only a few million years ago, and if they eventually fade away over time, then our galaxy might have experienced similar outbursts repeatedly throughout its evolution. This connects the Fermi bubbles to a broader understanding of how galaxies evolve. Astronomers studying distant galaxies see evidence for powerful outflows and jets regularly, but these are typically associated with much younger, more active systems. The discovery of recent activity in our own mature galaxy suggests that even old, stable galaxies like the Milky Way can still experience dramatic events. The bubbles also reveal something important about the environment surrounding our galaxy. The Eros-Theta X-ray bubbles show that our galaxy sits within a hot, tenuous medium that extends far beyond the visible disk of stars. This circumgalactic medium, as astronomers call it, plays an important role in galaxy evolution by regulating the inflow and outflow of material. Understanding the Fermi bubbles is helping astronomers piece together the complex relationship between galaxies and their surrounding environments. The bubbles represent a fossil record of past activity, preserved in the form of high energy particles and magnetic fields that continue to emit radiation millions of years after the initial event. The mystery of the Fermi bubbles also highlights the importance of multi-wavelength astronomy. These structures are invisible in ordinary light, but prominent in gamma rays and X-rays. Only by combining observations across the electromagnetic spectrum can astronomers hope to understand the full complexity of these phenomena. As observations continue and theoretical models improve, astronomers are gradually piecing together the story of the Fermi bubbles, whether they result from black hole activity, stellar explosions, or some combination of both. They represent one of the most dramatic examples of past violence in our otherwise peaceful galaxy. The bubbles remind us that our cosmic home is far more dynamic than it appears to the casual observer. The Milky Way might look like a serene spiral of stars from the outside, but its history includes periods of intense activity that created structures visible across tens of thousands of light years. In studying these bubbles, we're not just learning about exotic astrophysical processes, we're uncovering the hidden history of our own galactic neighborhood. The Fermi bubbles are like cosmic archaeological artifacts, preserving evidence of events that shaped the galaxy we inhabit today. As Doug Finkbeiner noted when reflecting on the discovery, finding the Fermi bubbles was a complete surprise. It's a reminder that even in our own cosmic backyard, there are phenomena of enormous scale and significance that we're only just beginning to understand. The universe, it seems, still has plenty of secrets left to reveal, even in the places we thought we knew best. The gentle glow of gamma rays from these ancient structures continues to shine through space, carrying with it the story of our galaxy's violent past and the promise of new discoveries yet to come. In their mysterious light, we glimpse both the power of cosmic forces and the endless capacity of the universe to surprise us with wonders we never imagined existed. As we near the end of our cosmic journey, we encounter perhaps the most perplexing discovery of all 300 objects scattered across the deep universe that appear to defy our fundamental understanding of how galaxies form and evolve. These aren't exotic phenomena from distant realms. They're potentially among the very first galaxies that ever existed, shining with a brightness that shouldn't have been possible so soon after the birth of the universe. The story begins with Haojing Yan, an astronomy professor at the University of Missouri, who was methodically searching through images from the James Webb Space Telescope. He was using a tried and true technique called the dropout method, a clever way astronomers identify the most ancient objects in the universe by looking for sources that appear in redder wavelengths but completely vanish when observed in bluer light. This vanishing act, called the Lyman break, occurs when hydrogen gas absorbs ultraviolet light from distant galaxies. As these galaxies recede from us, due to the expansion of the universe, their light stretches toward redder wavelengths, a phenomenon called redshift. The more distant the galaxy, the higher its redshift, and the closer we're looking to the dawn of time itself. Yan expected to find a few interesting candidates in the Webb data. What he found instead was completely unprecedented. 300 objects shining far brighter than any early galaxy should have been able to manage. These mysterious objects are candidate galaxies in the early universe, Yan explains, meaning they could be very early galaxies. If even a few of these objects turn out to be what we think they are, our discovery could challenge current ideas about how galaxies formed in the early universe, the period when the first stars and galaxies began to take shape. To understand why this discovery is so startling, we need to think about what the early universe was like. In the first few 100 million years after the Big Bang, the cosmos was a much simpler place. There were no heavy elements beyond hydrogen and helium, no dust, no planets, and certainly no complex structures like mature galaxies. The first stars that formed in this primordial environment were massive, short-lived giants that quickly exploded as supernovae, seeding space with heavier elements. These early stellar generations were expected to be relatively inefficient at forming stars, and the galaxies they created should have been small, faint, and simple compared to the grand spiral and elliptical galaxies we see in the modern universe. Yet here were 300 objects that appeared to be shining as brightly as some of the most luminous galaxies in today's cosmos, despite existing when the universe was less than 1 billion years old. Some of these candidates boasted ultraviolet magnitudes of -23 or brighter, and stellar masses exceeding 30 billion times that of our Sun. The biggest surprise, notes Bangjing Tom Sun, the graduate student who led the analysis, is just how many of these objects we found. We expected maybe a handful of extremely bright early galaxies, but 300 candidates in just 4 small patches of sky suggests these objects might be much more common than we ever imagined. The team used 2 of Webb's most powerful instruments, the near-infrared camera and the mid-infrared instrument, both specifically designed to detect light from the most distant corners of space. The farther away an object is, the longer its light has been traveling to reach us, and during that cosmic journey, the expansion of the universe stretches that light into increasingly longer, redder wavelengths. This is why Webb's infrared capabilities are so crucial for studying the early universe. The visible light emitted by the first galaxies has been stretched so much by cosmic expansion that it now appears as infrared radiation by the time it reaches our telescopes. But identifying these objects is only the first step in a careful detective process. The team used a technique called spectral energy distribution, fitting to estimate the properties of their candidates, their distances, ages, and masses, based on how bright they appeared across different wavelengths. This method is informative but can't provide the precision needed for absolute certainty. The gold standard for confirming these discoveries is spectroscopy, where astronomers split the light from each object into its component wavelengths, like creating a rainbow, to look for specific spectral signatures that reveal an object's true nature. This process is painstakingly slow and requires precious telescope time, but it's the only way to be certain about what these mysterious objects really are. So far, the team has managed to confirm one of their candidates through spectroscopy. Object Fur 115D underscore Brett underscore Sears underscore 062, as it's technically designated, has been verified as a genuine early galaxy with a redshift of 8.679, comma meaning we see it as it existed just 570 million years after the Big Bang. This single confirmation validates their detection method, but one object isn't enough to draw definitive conclusions about early galaxy formation. This object alone is not enough. Sun acknowledges, we will need to make additional confirmations to say for certain whether current theories are being challenged. The implications of these discoveries extend far beyond simply finding bright galaxies in the early universe. If confirmed, they could force astronomers to completely rethink the timeline and mechanisms of cosmic evolution. Current models suggest that galaxy formation was a gradual process in the early universe, with small protogalaxies slowly merging and growing over hundreds of millions of years. But these 300 candidates suggest that some galaxies manage to grow massive and luminous much more quickly than theoretical models predict. This could mean that star formation in the early universe was far more efficient than we thought, or that there were processes at work that we don't yet understand. One possibility is that the first stars were fundamentally different from modern stars. Computer simulations suggest that stars in the primordial universe might have been much more massive than typical stars today, some potentially weighing hundreds of times more than our sun. These stellar giants would have burned brightly but briefly, producing enormous amounts of light before exploding as supernovae. Another theory suggests that the early universe experienced periods of incredibly intense bursty star formation, instead of the steady, measured star formation we see in most galaxies today. These early systems might have undergone episodes where vast amounts of gas collapsed simultaneously, creating stellar nurseries far more productive than anything in the modern cosmos. There's also the intriguing possibility that some of these bright objects aren't powered by star formation at all, but by supermassive black holes. Webb has already discovered numerous little red dots, compact objects in the early universe that appear to contain black holes millions of times more massive than our sun. If some of Yan's 300 candidates are actually early quasars powered by feeding black holes, it would raise equally challenging questions about how such massive black holes could have formed so quickly after the Big Bang. The discovery also highlights the incredible capabilities of the Webb telescope itself. Previous generations of space telescopes, including the remarkable Hubble Space Telescope, could detect only the very brightest galaxies from the early universe. Webb's unprecedented infrared sensitivity has opened up an entirely new window on cosmic dawn, revealing phenomena that were completely invisible to earlier instruments. Thank you, Webb. It's a $10 billion difference, joked Susan Casson, an astronomer at the Space Telescope Science Institute, comparing Webb's images to those from previous observatories. The difference is like having an optometrist flip a lens so that the blurred lines on an eye chart suddenly come into sharp focus. But with this new clarity comes new mysteries. The early universe, as revealed by Webb, is far more complex and active than astronomers had anticipated. Instead of the relatively quiet, gradual assembly of cosmic structures that models predicted, we're seeing evidence of violent, rapid processes that could build massive, luminous galaxies in record time. The research team is now working to obtain follow up spectroscopic observations for more of their candidates, focusing on the brightest and most promising sources. Each confirmation will help build a statistical sample large enough to determine whether these objects represent rare anomalies or evidence for fundamentally different processes in the early universe. The broader astronomical community is watching these developments with intense interest. If a significant fraction of the 300 candidates prove to be genuine early galaxies, it would represent one of the most significant challenges to current cosmological models since the discovery of dark energy. But even if most of the candidates turn out to be something else, perhaps more nearby galaxies disguised by cosmic dust or unusual objects we don't yet understand, the discovery process itself is valuable. Each false positive teaches astronomers something about the challenges of identifying truly ancient objects and helps refine the techniques used to study the early universe. The mystery of the 300 objects also demonstrates the iterative nature of astronomical discovery. Science doesn't usually progress through sudden revelations, but through the patient accumulation of evidence, the careful testing of hypotheses, and the gradual refinement of our understanding. Each new observation adds another piece to an enormously complex puzzle. As we continue to study these enigmatic objects, we're not just learning about the early universe, we're discovering the limits of our current knowledge and identifying the questions that will drive astronomical research for decades to come. Whether these 300 candidates represent the first glimpse of a new chapter in cosmic evolution or a fascinating collection of cosmic mimics, they've already succeeded in expanding our appreciation for the complexity and wonder of the universe's earliest epochs. In the end, these mysterious objects floating in the deep cosmos serve as a reminder that the universe is still full of surprises, still capable of challenging our most fundamental assumptions about how cosmic structures form and evolve. They represent the cutting edge of human knowledge, the places where our understanding meets the vast unknown, and they promise that the story of cosmic discovery is far from over. The 300 objects that shouldn't be there have become a testament to the power of careful observation, the importance of following unexpected leads, and the endless capacity of the universe to surprise and humble us with phenomena we never imagined possible. In their mysterious light, we glimpse both the limits of current knowledge and the thrilling possibility of discoveries yet to come. And so we find ourselves at the end of our journey through the cosmos's most perplexing mysteries. We've traveled from the edge of our own solar system to the farthest reaches of the observable universe, encountering phenomena that stretch our imagination and challenge our understanding of what's possible in the vast expanse of space. Tonight, as we draw this exploration to a close, it's worth taking a moment to reflect on what these discoveries mean, not just for science, but for us as conscious beings trying to make sense of our place in an endlessly surprising universe. When we began, we encountered Oumuamua, that strange visitor from another star system that tumbled through our solar neighborhood like a cosmic calling card. Its unusual acceleration and peculiar shape reminded us that even in our own backyard, the universe can produce objects that don't fit our expectations. It was a gentle introduction to the idea that the cosmos is far stranger and more varied than our theories often assume. From there, we discovered planets that shouldn't exist, worlds with the density of cotton candy floating in space, planets somehow surviving the death of their stars, worlds where the very rocks rain from metallic skies. Each of these discoveries forced us to expand our definition of what a planet can be, reminding us that nature is far more creative than our models had predicted. We witnessed the possible birth of black holes in the infinity galaxy, saw cosmic accidents that revealed hidden chemistry in distant atmospheres, and discovered black holes knocked over on their sides like cosmic bowling pins. Each phenomenon showed us that the universe operates on scales and through processes that dwarf anything in our earthly experience. We explored cosmic flashbulbs that outshine entire galaxies for milliseconds, mysterious objects more powerful than supernovas that don't fit any known category, and little red dots in the early universe that might represent forms of matter and energy we've never encountered before. These discoveries revealed that the cosmos is filled with events of almost unimaginable violence and beauty, processes that create and destroy on scales that challenge our ability to comprehend them. Perhaps most humbling of all, we learned that dark energy, the very force that controls the fate of everything that exists, might not be constant after all. This discovery suggests that even our most fundamental assumptions about the nature of reality might need revision. The universe, it seems, is not just stranger than we imagine, it may be stranger than we can imagine. Yet in cataloging these mysteries, we've also witnessed something remarkable about human nature itself. Despite our small size and brief lifespans, compared to cosmic scales, we've somehow managed to detect and study phenomena occurring across billions of light years and billions of years. We've built instruments sensitive enough to detect the whisper faint signals from objects so distant that their light began its journey to us before the Earth even existed. This represents something extraordinary about consciousness and curiosity. We are, as far as we know, arrangements of atoms that have somehow become aware of themselves and their place in the cosmos. We've used this awareness to peer into the deepest mysteries of existence, to ask questions about phenomena occurring on scales from subatomic particles to galaxy clusters, from microseconds to cosmic epochs. The mysteries we've explored tonight don't diminish us, they elevate us. Each puzzle solved reveals new puzzles to contemplate. Each question answered opens doors to questions we never knew existed. The universe's capacity to surprise and perplex us is matched only by our capacity to wonder and investigate. Consider the remarkable fact that we can sit here on a small planet orbiting an ordinary star in an unremarkable galaxy and somehow know about the existence of sideways black holes, cosmic flashbulbs, and mysterious objects at the edge of space and time. We can trace the effects of invisible dark energy, detect the signatures of planets thousands of light years away, and piece together the violent history written in gamma ray bubbles that span our entire galaxy. This ability to understand phenomena far beyond our direct experience represents one of the most extraordinary capabilities that has ever emerged in the universe. We are the cosmos becoming conscious of itself, asking questions about its own nature and history. The discoveries we've explored also remind us that the universe is not a static, finished thing, but a dynamic, evolving system where new phenomena are constantly emerging. Stars are born and die, galaxies collide and merge, mysterious objects flash into existence and disappear. Even the fundamental forces that govern reality might be changing over time. This means that the universe of tomorrow will be different from the universe of today, just as the universe of today is different from the universe of the past. We live in a cosmos that is constantly writing new chapters in its own story, and we have the remarkable privilege of being able to read some of those chapters as they're being written. Perhaps most importantly, these cosmic mysteries teach us humility. Despite all our scientific achievements, despite our sophisticated instruments and elegant theories, the universe continues to produce phenomena that surprise and baffle us. We are still, in many ways, cosmic children trying to make sense of a reality far grander and more complex than we can fully grasp. This humility is not a weakness, it's a strength. It keeps us curious, keeps us questioning, keeps us open to possibilities we haven't yet imagined. The moment we think we have the universe figured out is the moment we stop learning and growing. The mysteries we've encountered also connect us to something larger than ourselves. When we study Tabby's star or puzzle over the Fermi bubbles, we're participating in humanity's greatest collaborative endeavor, the attempt to understand the cosmos we inhabit. These investigations span generations, involve thousands of researchers across the globe, and represent our species' collective effort to make sense of existence itself. Each of the phenomena we've discussed tonight was discovered through the patient work of astronomers, physicists, and other researchers who dedicated their lives to pushing the boundaries of human knowledge. Their discoveries become part of humanity's shared understanding, adding to a body of knowledge that belongs to all of us. In studying these cosmic mysteries, we also gain perspective on our own existence. The same physical processes that create exotic planets and power cosmic flashbulbs also operate in our own bodies and our own world. The carbon in our cells was forged in the cores of ancient stars. The water in our oceans may have arrived on comets from the outer solar system, and the very atoms that make up our bodies were once scattered across interstellar space. We are not separate from the cosmos we study. We are part of it. Every discovery about the universe is in some sense a discovery about ourselves. When we map the structure of distant galaxies, we're exploring the environment that shaped the matter from which we're made. When we study the formation of planets, we're learning about the processes that led to the existence of our own world. This connection extends beyond just physical processes. The curiosity that drives us to ask questions about cosmic mysteries, the wonder we feel when contemplating the vast scales of space and time, the satisfaction we derive from solving puzzles about the nature of reality. These too are part of the universe's story. Consciousness, curiosity, and wonder are as much a part of cosmic evolution as star formation and galaxy collisions. As we conclude our journey through these cosmic mysteries, it's worth remembering that this is not really an ending, but a beginning. Each of the phenomena we've discussed represents active areas of research, with new discoveries being made regularly. The questions we've explored tonight will likely have new answers by the time you hear these words, and entirely new mysteries will have emerged to capture our attention and imagination. The universe has spent billions of years creating the conditions necessary for creatures like us to emerge, beings capable of contemplating cosmic mysteries and seeking to understand the nature of existence. In doing so, we become the universe's way of understanding itself. We are cosmic evolution, becoming self aware, matter organizing itself into forms capable of wonder and investigation. This is perhaps the most remarkable discovery of all, that the universe has somehow given rise to beings capable of appreciating its beauty, puzzling over its mysteries, and seeking to understand its deepest truths. In studying cosmic phenomena, we're not just passive observers, but active participants in the unfolding story of the cosmos itself. So, as we close this exploration of NASA's strangest space discoveries, we're left not with answers, but with a renewed sense of wonder and curiosity. The universe continues to unfold its mysteries before us, continues to surprise and perplex us, continues to invite us deeper into questions we're only just learning how to ask. The mysterious visitors, impossible planets, sideways black holes, and ancient objects that shouldn't exist are all part of a cosmos far richer and more wonderful than we ever imagined. They remind us that reality is always stranger than fiction, that the universe's capacity for creativity and surprise is boundless, and that our journey of discovery has only just begun. In the end, perhaps that's the most important lesson these cosmic mysteries teach us, that wonder never ends. Questions always lead to more questions, and the universe will always have more secrets to share with those patient and curious enough to seek them out. The gentle conclusion is that there is no conclusion, only the endless, beautiful process of discovery, the eternal conversation between conscious beings and the cosmos that gave birth to consciousness itself. And in that conversation, we find not just knowledge about the universe, but something even more precious. We find our place within it, our role as participants in the greatest story ever told, the story of the universe coming to know itself